Hello there, and welcome to the Sleep Science channel. Tonight, we'll be taking an epic journey into the wonders, mysteries, and marvels of our universe. Science has made remarkable progress in revealing this immense frontier. We've mapped galaxies, measured ripples in spacetime, and uncovered the behavior of invisible yet powerful forces. But for every advance we make, more questions arise. The universe keeps its secrets well, and many of the ideas we've come to rely on may only be the first step of a much deeper reality. Space may be stranger than our models suggest. Time might not behave the way we assume, and even the foundations of matter and energy might just be fragments of a much grander theory. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Take a deep breath, allow your shoulders to soften, and let the day fade away as we explore our amazing universe together. Let's begin. The Big Bang, the universe began in a moment so brief and so intense that our minds can barely grasp it. More than 13 billion years ago, everything we know was compressed into a space smaller than an atom. There was no before, there was no outside. Time itself began with this event we call the Big Bang. In that first instant, space expanded faster than the speed of light, carrying with it the seeds of all that would come. Energy condensed into particles, particles gathered into atoms, and atoms eventually formed the stars and galaxies we see today. The Big Bang was not an explosion in space, but an expansion of space itself. Every point in the universe was part of the beginning, and every point has been moving apart ever since. The universe doesn't have a center, because all of space emerged at once. We live within the afterglow of that ancient fire, surrounded by its gentle light, even now. To imagine the beginning is to touch infinity with your thoughts, to feel the weight of time stretching backward to the first heartbeat of creation. The first moments, in the earliest fractions of a second, the universe underwent dramatic changes. Energy transformed into matter and antimatter, which immediately annihilated each other in bursts of light. Yet a tiny imbalance existed, a slight excess of matter over antimatter. This imperfection saved the universe. Without it, everything would have destroyed itself, leaving only radiation behind. That fragile difference allowed particles to survive, eventually forming all the structures we observe today. During these first moments, the universe was unimaginably hot. Temperatures exceeded trillions of degrees, conditions so extreme that the fundamental forces of nature behaved differently. Gravity, electromagnetism, and nuclear forces may have been unified into a single force. As the universe expanded and cooled, these forces separated, each taking on the distinct character we measure today. Those first instants shaped the physical laws that govern stars, planets, and life itself. Everything we know emerged from that brief, violent beginning. Cosmic inflation. Shortly after the Big Bang, the universe experienced a period of incredible growth called cosmic inflation. In less than a trillionth of a second, space expanded by a factor greater than we can easily express. Regions that were once close enough to touch were suddenly separated by distances larger than galaxies. This rapid expansion solved several puzzles about the universe's structure. It explains why the cosmos looks roughly the same in every direction, and why space appears to be flat rather than curved. Inflation also amplified tiny quantum fluctuations, stretching them to enormous scales. These fluctuations became the seeds of all future structure. Where space was slightly denser, gravity eventually pulled matter together, forming the first stars and galaxies. The ripples from inflation are still visible today in the cosmic microwave background, a faint glow that fills all of space. This ancient light carries the imprint of those early fluctuations, a map of the universe when it was still young and simple. Cosmic microwave background. If you could tune your eyes to see microwave light, you would discover that the entire sky glows softly. This faint glow is called the cosmic microwave background. It is the oldest light in the universe, released when the cosmos was only 380,000 years old. Before that moment, the universe was too hot and dense for light to travel freely. Photons scattered endlessly through a thick fog of particles. But as space expanded and cooled, atoms formed, and light was finally free to move. That ancient light has been traveling ever since, stretched by billions of years of cosmic expansion into gentle microwaves. When we observe this glow, we are seeing the universe as it was in its infancy. The tiny variations in its temperature map the earliest structures, the seeds that would grow into galaxies, stars, and planets. This soft radiation fills all of space, a quiet whisper from the dawn of time. It reminds us that the universe has memory, that every moment leaves traces we can still detect. The Dark Ages. After the cosmic microwave background was released, the universe entered a period known as the Dark Ages. For hundreds of millions of years, no stars existed. The cosmos was filled with neutral hydrogen gas, slowly drifting in darkness. Gravity worked patiently during this time, drawing matter into clumps that would eventually collapse and ignite. These were quiet ages, a cosmic pause between the brilliance of the Big Bang and the first starlight. During the Dark Ages, the universe was simpler than it is today. There were no galaxies, no planets, no light to illuminate the vast expanses of space. Yet this period was essential. The structures that formed during these ages laid the foundation for everything that followed. Slowly, the densest regions grew heavier, pulling in more gas until they reached the point where stars could be born. The Dark Ages ended, not with a sudden flash, but with a gradual awakening as the first stars began to shine. The first stars changed everything. When they ignited, their light pushed back the darkness that had filled the universe for so long. These early stars were massive, perhaps hundreds of times heavier than our sun. They burned with incredible intensity, releasing energy that transformed their ultraviolet light began to ionize the hydrogen gas around them, creating bubbles of ionized material that grew larger over time. As more stars formed, these bubbles expanded and merged. Eventually, the entire universe became rayonized, transparent to light once again. This period is called the Epoch of Reionization, a second great transformation after the release of the cosmic microwave background. The first stars also forged the first heavy elements, scattering them into space when they exploded as supernovas. These elements would seed the next generation of stars, enriching the cosmos with the building blocks needed for planets and life. In the first few minutes after the Big Bang, the universe was hot enough for nuclear fusion to occur throughout all of space. Protons and neutrons combined to form the lightest elements: hydrogen, helium, and tiny amounts of lithium. This process, called Big Bang nucleosynthesis, created the primordial composition of the universe. About 75% of the matter became hydrogen, and most of the rest became helium. These are still the most abundant elements in the cosmos today. Everything heavier than lithium was created later, inside stars. When stars burn, they fuse lighter elements into heavier ones. Carbon, oxygen, nitrogen, silicon, iron, all were forged in stellar cores through billions of years of nuclear reactions. The heaviest elements, like gold and uranium, require even more extreme conditions. They form in supernova explosions, or when neutron stars collide. Every element in your body, except hydrogen, was created in a star. We are not separate from the universe, but made from its ashes, shaped by its fires, born from its oldest processes. As the universe expanded, it cooled. In the beginning, temperatures were so high that atoms could not hold together. Electrons moved too quickly, constantly torn away from nuclei by violent collisions. But as space grew, the energy spread thin. Temperatures dropped gradually, allowing particles to slow down. Eventually, conditions became gentle enough for atoms to form and remain stable. This cooling was not uniform or sudden, but a slow transformation that took hundreds of thousands of years. The cooling universe passed through distinct phases, like water changing from steam to liquid to ice. Each phase brought new possibilities. When atoms formed, light could travel freely. When the first stars ignited, they reheated small regions of space. When galaxies gathered, they created islands of warmth in the cooling void. Even today, the universe continues to cool as space expands. In the far future, it may reach temperatures close to absolute zero, becoming a cold and quiet place. But for now, it still carries warmth from its fiery beginning. The early universe was not perfectly smooth. Tiny variations in density existed from the very beginning, perhaps seeded by quantum fluctuations during inflation. Where matter was slightly denser, gravity pulled more material inward. Where it was less dense, matter drifted away. Over millions of years, these small differences grew into large structures. Dense regions became denser, while empty regions became emptier. This process carved the cosmos into the web-like pattern we observe today. The first structures to form were small, perhaps only a few thousand times the mass of our sun. These collapsed first, merging together to form larger objects. Gradually, through countless mergers and interactions, galaxies emerged. The process was chaotic, driven by gravity's patient pull. Some regions became rich with matter, forming clusters of galaxies. Others remained sparse, creating vast cosmic voids. This structure continues to evolve, shaped by dark matter and dark energy, forces we detect but do not fully understand. Time began before the Big Bang. There was no time. This statement feels strange because we think of time as something that has always existed, but according to our best theories, time itself began with the universe. There was no ticking clock before the first moment, no sequence of events waiting to unfold. Time emerged along with space, energy, and matter. To ask what happened before the Big Bang may be meaningless, like asking what lies north of the North Pole. This idea challenges our intuition. We live in a world where every event has a cause, where time flows steadily from past to future. Yet the universe itself may not have a cause in the usual sense. It may simply be existing without needing something prior. Some theories suggest that time could be cyclic, with the universe expanding and contracting in endless rhythm. Others propose a multiverse where many universes exist, each with its own beginning. We do not yet know. The origin of time remains one of the deepest mysteries, touching the very edge of what science can explore. The expanding cosmos. The universe is not static. Every galaxy is moving away from every other galaxy, carried by the expansion of space itself. This was one of the great discoveries of the 20th century. Distant galaxies appear redshifted, their light stretched to longer wavelengths by the growing distances between us. The farther a galaxy is, the faster it recedes. This expansion is not objects moving through space, but space itself growing larger, like dots on an inflating balloon. The expansion began with the Big Bang and continues today. For a long time, scientists thought gravity might slow this expansion, perhaps even reversing it. But observations revealed something unexpected. The expansion's accelerating. Some mysterious force, called dark energy, is pushing space apart faster and faster. We do not know what dark energy is, only that it dominates the universe's energy budget. This acceleration means that distant galaxies will eventually move beyond our reach, their light never able to catch up with expanding space. The universe is not only vast, but growing vaster with every passing moment. Stellar nurseries, stars are born in cold, dark clouds of gas and dust that drift through galaxies. These clouds are called molecular clouds, vast regions where temperatures drop to just a few degrees above absolute zero. Inside these frigid environments, gravity slowly pulls material together. When enough gas gathers in one place, it begins to collapse under its own weight. The collapse is slow at first, taking millions of years, but it gradually accelerates as the clump grows denser. As the material falls inward, it heats up. The center becomes a glowing core, a protostar, not yet bright enough to be called a true star. Around it, a disk of gas and dust forms, swirling like water around a drain. This disk will eventually form planets, moons, and asteroids. But first, the protostar must continue gathering mass. When the core becomes hot and dense enough, nuclear fusion ignites. Hydrogen atoms fuse into helium, releasing enormous energy. At that moment, a star is born, shining with light that pushes back the darkness of the cloud that created it. The first stars. The first stars were unlike anything we see today, born from pure hydrogen and helium in a universe without heavy elements. These ancient suns burned with incredible intensity. Some may have been hundreds of times more massive than our sun, blazing fiercely across the early darkness. They lived fast and died young, collapsing in powerful explosions after only a few million years. These first supernovas forged the first heavy elements, carbon, oxygen, iron, and scattered them into space. The first stars. Without these pioneering stars, there would be no planets, no oceans, no life. Every atom in your body was created in the heart of a star or in the violence of its death. The iron in your blood, the calcium in your bones, the oxygen in your breath, all were born in stellar furnaces long before Earth existed. We are made of stardust, not as poetry, but as scientific truth. The first stars gave the universe its complexity, enriching space with the ingredients needed for everything that followed. Types of stars. Stars come in many varieties, each with its own character and destiny. The smallest stars, red dwarfs, are cool and dim, burning their fuel so slowly they can shine for trillions of years. Our sun is a medium-sized star, a yellow dwarf that will burn steadily for about 10 billion years. Larger stars burn hotter and faster, exhausting their fuel in just millions of years. The most massive stars are blue giants, blazing with fierce intensity but destined for brief and violent lives. The color of a star tells us its temperature. Cool stars glow red, while hot stars shine blue or white. The mass of a star determines its fate. Small stars end their lives quietly, fading into white dwarfs. Medium stars, like our sun, expand into red giants before shedding their outer layers and leaving behind glowing cores. Massive stars explode as supernovas, creating neutron stars or black holes. Each type of star plays a role in the cosmic cycle, creating and distributing elements, lighting the darkness, and shaping the galaxies that contain them. Star formation. Star formation is a delicate balance between gravity and other forces. Gravity pulls gas together, trying to create dense clumps. But other forces resist. Gas pressure pushes outward. Magnetic fields thread through the clouds, and turbulence stirs the material. For a star to form, gravity must overcome these opposing forces. This happens most easily in cold, dense regions where gas moves slowly and cannot resist collapse. When part of a cloud becomes unstable, it begins to fall inward. The collapse is not smooth or predictable. The cloud fragments into many pieces, each collapsing on its own. This is why stars rarely form alone. They are born in groups, often hundreds or thousands at a time. These stellar nurseries are messy, chaotic places filled with glowing gas, jets of material, and newborn stars still wrapped in the remnants of their birth clouds. Over time, the radiation from young stars clears away the gas, revealing the cluster. Some stars remain bound together, while others drift apart, carrying memories of their shared beginning into the wider galaxy. Before a star truly shines, it exists as a protostar, a warm, glowing object, not yet capable of sustained fusion. A protostar forms when a collapsing cloud reaches a certain density. The center heats up from the compression, glowing with infrared light hidden inside thick layers of dust. The protostar continues to gather material from the surrounding cloud, growing heavier and hotter. This phase can last for hundreds of thousands of years. During this time, the protostar is turbulent and unstable. It may eject jets of material from its poles, driven by magnetic fields. These jets can stretch for light years, creating glowing shocks when they collide with surrounding gas. The protostar also develops a rotating disk of material around it, the birthplace of future planets. Eventually, when the core temperature reaches about 10 million degrees, hydrogen fusion begins. The protostar becomes a true star, entering a stable phase that may last billions of years. This transformation marks the beginning of the star's main life, a long period of steady burning, nuclear fusion at the heart of every star. Nuclear fusion transforms mass into energy. Deep in the core, temperatures and pressures are so extreme that hydrogen nuclei overcome their natural repulsion and fuse together. For hydrogen nuclei combine to form one helium nucleus, a process that releases tremendous energy. This energy travels outward, eventually reaching the surface and radiating into space as light and heat. The star shines because of this constant fusion, a controlled reaction that has continued for billions of years. The energy produced by fusion creates an outward pressure that balances gravity's inward pull. This balance keeps the star stable, preventing it from collapsing or exploding. As long as hydrogen remains in the core, the star continues burning steadily. Different stars fuse hydrogen at different rates. Massive stars burn quickly, exhausting their fuel in millions of years. Small stars burn slowly, potentially shining for longer than the current age of the universe. This fusion is the engine that powers stars, the source of all their light, and the process that creates the elements needed for planets and life. Main sequence stars. Most stars spend the majority of their lives in a phase called the main sequence. During this time, they burn hydrogen steadily in their cores, maintaining a balance between gravity and the outward pressure from fusion. Our Sun is currently a main sequence star, about halfway through its 10 billion year lifetime. Main sequence stars vary widely in size, temperature, and brightness, but they all share the same basic process: hydrogen fusing into helium in their cores. The main sequence is not a physical location, but a stage of stellar evolution. When astronomers plot stars on a graph of brightness versus temperature, most fall along a diagonal band. This band is the main sequence, representing stars in their stable, hydrogen-burning phase. A star's position on the main sequence depends on its mass. Massive stars sit at the top, hot and luminous. Small stars sit at the bottom, cool and dim. This phase is the longest period of a star's life, a time of stability and steady output that shapes the environments of any planets that orbit nearby. Red giants. When a star exhausts the hydrogen in its core, it enters a new phase. The core contracts under gravity, heating up and causing the outer layers to expand dramatically. the star becomes a red giant, a bloated version of its former self with a cool, luminous surface. These giants can grow so large that they swallow the orbits of inner planets. Our sun will become a red giant in about 5 billion years, expanding to engulf Mercury and Venus, and perhaps even Earth. Inside a red giant, new fusion processes begin. Helium in the core fuses into carbon and oxygen, releasing energy that prevents further collapse. The outer layers are now so distant from the core that they barely hold on, slowly puffing away into space. This creates beautiful structures called planetary nebulae, glowing shells of gas lit by the hot core inside. Red giants are unstable, pulsating and shedding material. They represent the beginning of the end for medium-sized stars, a dramatic transformation before they fade into quiet white dwarfs. Red giants. Supergiants. The most massive stars evolve into supergiants, enormous objects that dwarf ordinary red giants. These stars can be hundreds of times larger than the sun, their surfaces reaching far beyond where Earth orbits. Supergiants burn through their fuel at incredible rates, fusing heavier and heavier elements in their cores. They create carbon, oxygen, neon, silicon, and eventually iron. Each new element requires higher temperatures to fuse, and each fusion stage lasts a shorter time. A supergiant's life is a race against gravity. As it fuses heavier elements, the core becomes increasingly unstable. Iron cannot be fused to release energy, so when the core turns to iron, the star's end is near. Without fusion to generate outward pressure, the core collapses in a fraction of a second. The collapse is catastrophic, triggering a supernova explosion that tears the star apart. The outer layers are flung into space at tremendous speeds, while the core may become a neutron star or black hole. Supergiants are short-lived, but incredibly influential, enriching galaxies with heavy elements and creating some of the most spectacular events in the universe. White dwarfs, when medium-sized stars like our sun shed their outer layers, they leave behind a dense core called a white dwarf. This remnant is about the size of Earth, but it contains a significant fraction of the star's original mass. White dwarfs no longer produce energy through fusion. Instead, they glow with leftover heat, slowly cooling over billions of years. Their surfaces can be extremely hot at first, tens of thousands of degrees, but they gradually fade as their heat radiates into space. White dwarfs are incredibly dense. A teaspoon of white dwarf material would weigh several tons on Earth. This density is supported not by fusion or normal pressure, but by a quantum mechanical effect called electron degeneracy pressure. The electrons in the dwarf are packed so tightly that they resist further compression. This pressure keeps the star from collapsing under its own gravity. Over trillions of years, a white dwarf will cool completely, becoming a black dwarf, a cold, dark remnant. No black dwarfs exist yet, because the universe is not old enough for any white dwarf to have cooled completely. Stellar cluster stars are often born in groups called clusters. These can range from loose associations of a few dozen stars to dense globular clusters containing hundreds of thousands. Open clusters form in the disk of galaxies from the same molecular cloud. The stars in these clusters are young, often still surrounded by remnants of the gas that formed them. Over time, gravitational interactions in the pool of the galaxy cause open clusters to disperse. Most stars, including our sun, were likely born in such clusters before drifting apart. Globular clusters are different. These are ancient, spherical collections of stars orbiting in the halos of galaxies. Their stars are old, formed in the early universe when galaxies were still assembling. Globular clusters are tightly bound by gravity, dense enough that stars occasionally collide or pass close to one another. Studying these clusters helps astronomers understand stellar evolution and the history of galaxies. Each cluster is a time capsule, preserving stars from a much earlier era, giving us a glimpse into the conditions that existed billions of years ago. Life cycles. Every star follows a life cycle determined by its mass. Medium stars like our sun shine for billions of years, then swell into red giants before shedding their outer layers and leaving behind dense cores. Massive stars live fast, burning their fuel in just millions of years, then exploding as supernovas and leaving behind neutron stars or black holes. Each stage has its own character, its own beauty, its own contribution to the cosmos. The life cycle of stars is also the life cycle of matter. Stars create elements, disperse them through space, and provide the raw material for new stars and planets. This cycle has repeated countless times since the first stars formed. Each generation of stars is enriched by the deaths of previous generations. Our sun is a third or fourth generation star, built from gas that once belonged to earlier suns. The cycle continues, driven by gravity, fusion, and the flow of time. It is a process without beginning or end, a cosmic rhythm that shapes the universe. What is a galaxy? A galaxy is a vast collection of stars, gas, dust, and dark matter, bound together by gravity. Galaxies come in many shapes and sizes. Some are spirals, like our Milky Way, with graceful arms winding outward from a central bulge. Others are elliptical, shaped like smooth, glowing spheres or footballs. Still others are irregular, lacking clear structure, their forms shaped by collisions or interactions with neighbors. Each galaxy contains billions or even trillions of stars, along with nebulae where new stars are born. Galaxies are not static. They rotate, evolve, and interact with their stars orbit the galactic center, taking millions of years to complete a single loop. Gas flows inward, fueling star formation, while supernova explosions blow material outward. Galaxies can merge, creating larger systems. They can be torn apart by tidal forces. Despite their immense size, galaxies are dynamic, alive with motion and change. They are the building blocks of the universe, islands of light separated by vast dark spaces, yet connected through gravity in the web of cosmic structure. Spiral galaxies are among the most beautiful structures in the universe. They have a flat disk of stars, gas, and dust, with spiral arms winding outward from a central bulge. The arms are not solid structures, but density waves, regions where stars and gas are slightly more concentrated. As material moves through these waves, it is compressed, triggering bursts of star formation. The young, hot stars light up the arms, making them appear bright and blue. Between the arms, older stars continue their orbits, less visible, but still present. Spiral galaxies are common in the universe, especially among younger, gas-rich systems. Over time, spirals can exhaust their gas or merge with other galaxies, transforming into elliptical systems. Elliptical galaxies. Elliptical galaxies are smooth, featureless collections of stars shaped like elongated spheres. Unlike spirals, they have little gas or dust, and very little ongoing star formation. Most of their stars are old, giving them a yellowish or reddish color. Elliptical galaxies range from small dwarfs containing just a few million stars to giant ellipticals with trillions. The largest galaxies in the universe are ellipticals. sitting at the centers of massive galaxy clusters. These galaxies likely formed through mergers. When two spiral galaxies collide, their gas is used up in bursts of star formation, and their disks are destroyed. What remains is a smooth, elliptical distribution of stars. The stars move in random orbits, not the ordered rotations seen in spirals. Elliptical galaxies are quieter than spirals, lacking the vibrant star-forming regions. Yet they are important, representing the end state of galactic evolution. Many galaxies will eventually become ellipticals as the universe ages and mergers become more common. The Milky Way, we live inside a galaxy called the Milky Way. It is a barred spiral containing hundreds of billions of stars, along with vast clouds of gas and dust. From our position within the disk, we see the galaxy as a band of light stretching across the night sky. This band is the combined glow of billions of stars, too distant to see individually. The name Milky Way comes from its appearance, a milky, hazy streak that ancient observers thought resembled spilled milk across the heavens. Our solar system orbits about halfway out from the center, in a relatively quiet region between spiral arms. It takes about 230 million years to complete one orbit around the galaxy. The Milky Way is not alone. It belongs to a small group of galaxies called the Local Group, which includes the Andromeda Galaxy and about 50 smaller companions. In a few billion years, the Milky Way and Andromeda will collide and merge, creating a new, larger galaxy. For now, our galaxy remains a beautiful spiral, slowly turning in the darkness, carrying us along on its ancient journey. Galactic centers at the heart of most large galaxies lies a supermassive black hole. These black holes contain millions or billions of times the mass of the Sun, packed into a region smaller than our solar system. They formed in the early universe, perhaps from the collapse of massive gas clouds or from the mergers of smaller black holes. Over time, they grew by consuming gas, dust, and even stars that wandered too close. Despite their enormous mass, they occupy only a tiny fraction of the galaxy's volume. The Milky Way's central black hole is called Sagittarius A*. It has a mass of about 4 million suns. Most of the time, it is quiet, emitting only faint radiation, but occasionally, gas falls toward it, forming a hot, glowing disk that releases intense energy. In other galaxies, central black holes can be much more active, creating brilliant quasars that outshine their entire galaxies. These central engines shape the galaxies around them, influencing star formation, gas flows, and the motion of stars near the core. They are both creators and destroyers, powerful forces hidden in the hearts of galaxies. Dark matter halos galaxies are surrounded by vast halos of dark matter, an invisible substance that does not emit or absorb light. We cannot see dark matter directly, but we know it exists because of its gravitational effects. Stars in the outer regions of galaxies move faster than they should if only visible matter were present. This extra speed indicates the presence of additional mass, a halo of dark matter extending far beyond the visible stars. These halos are much larger than the galaxies themselves, containing several times more mass than all the stars and gas combined. Dark matter shaped the formation of galaxies. In the early universe, dark matter clumped together first, creating gravitational wells into which ordinary matter fell. Gas collected in these wells, cooled, and formed stars. Without dark matter, galaxies, as we know them, could not exist. The nature of dark matter remains one of the great mysteries of science. It could be exotic particles, or perhaps something even stranger. For now, it remains hidden, detectable only through gravity, a silent scaffold holding galaxies together. Galaxy clusters, galaxies do not drift alone through space. They gather into groups and clusters, bound together by gravity. Our Milky Way belongs to the Local Group, a small collection of about 50 galaxies. Larger clusters can contain thousands of galaxies, all orbiting a common center. The space between galaxies in a cluster is not empty. It is filled with hot gas, heated to millions of degrees by the gravitational energy of the cluster. This gas emits X-rays, glowing faintly in wavelengths invisible to human eyes. The largest galaxy clusters are some of the most massive structures in the universe. They can contain more mass than 1,000,000 billion suns, most of it in the form of dark matter. Within clusters, galaxies interact frequently. They can collide, merge, or pass close enough to strip gas and stars from one another. These interactions reshape galaxies, transforming spirals into ellipticals and triggering bursts of star formation. Galaxy clusters also serve as laboratories for studying dark matter and dark energy, helping astronomers understand the forces that govern the universe on the largest scales. Superclusters, even galaxy clusters, are not the largest structures. Clusters themselves gather into superclusters, vast filaments and sheets of galaxies stretching across hundreds of millions of light. Our local group is part of the Virgo supercluster, which contains dozens of galaxy clusters and groups. Superclusters are not tightly bound by gravity. They are more like the scaffolding of the universe, tracing the large-scale distribution of matter. Between superclusters lie enormous voids, regions with very few galaxies, creating a cosmic web of matter and emptiness. The cosmic web is the largest known structure in the universe. It emerged from the tiny density variations present in the early universe, amplified by billions of years of gravitational growth. Dark matter forms the backbone of this web, with galaxies and gas tracing its filaments. The pattern is surprisingly similar across the universe, suggesting that the same physical laws operate everywhere. Studying the cosmic web helps us understand how structure formed and evolved, how galaxies are distributed, and how the universe's expansion affects the largest scales. Cosmic voids between the filaments of the cosmic web lie vast, empty regions called cosmic voids. These voids can span hundreds of millions of light years, containing very few galaxies. They are not completely empty, but they are remarkably underdense compared to the filaments in clusters. The largest voids are among the biggest structures in the universe, enormous bubbles of near emptiness surrounded by walls of galaxies. The existence of voids is a natural consequence of cosmic structure formation. As matter gathered into dense regions, it left behind empty spaces. In the void, the environment is different from the rest of the universe. Galaxies are rare and often small. There is less interaction, less star formation, and a quieter existence. Some theories suggest that voids expand faster than the average universe, pushed outward by the lower density within them. Voids also provide a unique laboratory for studying dark energy, the mysterious force causing the universe's expansion to accelerate. By measuring how voids evolve, astronomers can learn about the nature of this force. Voids remind us that the universe is not uniform, but a rich tapestry of structure and emptiness. The cosmic web, when astronomers map the positions of galaxies across vast distances, a striking pattern emerges. Galaxies are not scattered randomly, but arranged in a web-like structure. Long filaments of galaxies stretch across space, connecting dense clusters. Between the filaments lie enormous voids, regions with very few galaxies. This pattern is called the cosmic web, and it represents the largest scale structure in the universe. The web formed from tiny fluctuations in the early universe, amplified by gravity over billions of years. The cosmic web is shaped primarily by dark matter. Dark matter clumped together first, creating the gravitational framework. Ordinary matter, the gas and stars we can see, followed the dark matter, collecting in the deepest gravitational wells. The result is a universe that looks almost biological, with threads and nodes resembling neurons or blood vessels. This structure is not static. It continues to evolve as gravity pulls matter together and dark energy pushes space apart. The cosmic web is the universe's skeleton, the hidden architecture that organizes everything we observe. Galactic collisions. Galaxies sometimes collide. These collisions are not violent crashes where stars smash together. Space is so vast that individual stars almost never hit each other. Instead, the galaxies pass through one another, their stars and gas mixing over millions of years. Gravity pulls the galaxies together, stretching them into long tidal tails and distorting their shapes. Gas clouds collide, compressing and triggering intense bursts of star formation. The result is a chaotic, beautiful transformation that can last for billions of years. When two spiraled galaxies merge, the outcome depends on their sizes and the angle of collision. Often, the merger destroys the spiral structure, creating an elliptical galaxy. Sometimes, gas is funneled toward the center, feeding the supermassive black holes and creating bright quasars. Our Milky Way will collide with the Andromeda Galaxy in about 4 billion years. The merger will reshape both galaxies, creating a new, larger system. Collisions are a key part of galactic evolution, helping galaxies grow and transforming their structure over cosmic time. Active galactic nuclei. Some galaxies have incredibly bright centers called active galactic nuclei. These cores outshine all the stars in the galaxy combined, powered by supermassive black holes consuming enormous amounts of gas. As material spirals toward the black hole, it heats up, emitting intense radiation across the electromagnetic spectrum. The brightest of these are called quasars, visible from billions of light years away. Quasars are more common in the distant, early universe, suggesting that galaxies were more active in the past. Active galactic nuclei can affect their entire galaxies. The energy they emit can heat gas, preventing it from cooling and forming new stars. Jets of particles can be launched from the vicinity of the black hole, traveling thousands of light years into space. These jets create enormous lobes of radio emission, visible to radio telescopes. The activity eventually fades as the black hole exhausts its supply of nearby gas. The galaxy quiets, and the black hole becomes dormant. Our own Milky Way once may have had an active nucleus, but today its central black hole is mostly quiet. What are black holes? Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. They form when massive amounts of matter collapse into an incredibly small volume. This collapse creates a boundary called the event horizon, a point of no return. Anything that crosses the event horizon is pulled inexorably toward the center, never to emerge again. Outside the horizon, space behaves normally, but inside, the rules change. Time and space twist in ways that challenge our understanding. Black holes come in different sizes. Stellar black holes form when massive stars collapse at the end of their lives. They typically contain a few times the mass of the sun. Supermassive black holes, found at the centers of galaxies, contain millions or billions of solar mass. We do not fully understand how these giants formed, though they likely grew by consuming gas and merging with other black holes. Despite their fearsome reputation, black holes are not cosmic vacuum cleaners. They only affect objects that come very close. From a distance, their gravity is no different from any other massive object. Event horizons. The event horizon is the defining feature of a black hole. It is the boundary beyond which escape becomes impossible. The event horizon is not a physical surface, but a mathematical boundary, a point where the escape velocity equals the speed of light. Once something crosses this boundary, it cannot send signals or light back to the outside universe. To an outside observer, an object approaching the horizon appears to slow down, freeze, and fade as its light becomes increasingly red. Time itself seems to stop at the horizon. The size of the event horizon depends on the black hole's mass. A black hole with the mass of the Sun would have a horizon only about 3 kilometers in radius. A supermassive black hole could have a horizon larger than our solar system. The event horizon hides the interior from view, creating a one-way membrane through which information flows inward but never outward. What happens inside remains one of the greatest mysteries in physics. Our theories break down near the center, where gravity becomes infinitely strong. The event horizon protects the outside universe from this singularity, cloaking it in darkness. Spacetime, curvature. Black holes warp spacetime in extreme ways. According to Einstein's theory of general relativity, mass and energy curve the fabric of spacetime, and objects follow the curves. Near a black hole, spacetime curves so sharply that even light cannot travel in straight lines. Paths that would normally lead away from the black hole bend back toward it. This curvature is not just a distortion of space but also of time. Clocks near a black hole tick more slowly compared to clocks far away. This bending of spacetime creates effects that seem impossible. Light orbits the black hole at a certain distance, neither escaping nor falling in. This creates a photon sphere, a shell where photons circle endlessly. Inside the event horizon, all paths lead toward the center. In this region, moving toward the center is as inevitable as moving forward in time. The curvature becomes so extreme that space and time exchange roles. Describing what happens inside requires mathematics that push the boundaries of our understanding. Black holes are laboratories where the laws of physics are tested to their limits. Stellar black holes. Stellar black holes form from the remnants of massive stars. When a star much heavier than the Sun exhausts its nuclear fuel, its core collapses catastrophically. If the core is massive enough, nothing can stop the collapse. The core shrinks past the neutron star stage, continuing to compress until it forms a black hole. The outer layers of the star may explode as a supernova, or they may fall inward, swallowed by the newly formed black hole. The result is an object of incredible density, containing several solar masses within a region just a few kilometers across. Stellar black holes are difficult to detect because they emit no light. Astronomers find them by observing their effects on nearby matter. If a black hole is part of a binary system, it can pull gas from its companion star. This gas spirals inward, heating to millions of degrees and emitting X-rays before crossing the event horizon. These X-ray binaries are some of the brightest sources in the X-ray sky. By studying them, we learn about black hole behavior, accretion, and the extreme physics near the event horizon. Stellar black holes are not rare. Our galaxy likely contains millions of them, most drifting silently through space. Supermassive black holes. At the center of most large galaxies lies a supermassive black hole, containing millions or even billions of times the mass of the Sun. These giants are fundamentally different from stellar black holes, not just in size, but in origin. They formed in the early universe, possibly from the direct collapse of massive gas clouds or from the mergers of smaller black holes. Over billions of years, they grew by consuming gas, dust, and stars that wandered too close. Their growth is tied to the evolution of their host galaxies. Supermassive black holes are both destructive and creative. When they feed, they emit enormous energy, creating quasars and active galactic nuclei that can outshine their entire galaxies. Jets launched from their vicinity can influence star formation across the galaxy, heating gas and preventing it from cooling. Yet they also play a role in shaping galactic structure. The mass of a galaxy's central black hole is correlated with properties of the galaxy itself, suggesting a deep connection between the two. These giants are not just passengers, but active participants in cosmic accretion disks. When gas falls toward a black hole, it does not plunge straight in. Angular momentum causes it to spiral, forming a flat, rotating disk called an accretion disk. Friction within the disk heats the gas to extreme temperatures, causing it to glow brightly. The inner regions of the disk can reach millions of degrees, emitting X-rays and ultraviolet light. This makes accretion disks some of the brightest objects in the universe. Even though the black hole itself remains dark, the behavior of accretion disks depends on the rate at which matter falls in. If the inflow is slow, the disk is thin and hot, radiating efficiently. If the inflow is rapid, the disk becomes thick and turbulent, driving powerful winds and jets. Material in the disk gradually loses angular momentum and spirals closer to the black hole. At the innermost stable orbit, just outside the event horizon, particles make their final plunge. Studying accretion disks helps astronomers understand black hole feeding, energy release, and the physics of matter under extreme conditions. Gravitational waves, when two black holes spiral together and merge. They create ripples in spacetime called gravitational waves. These waves travel at the speed of light, carrying information about the collision across the universe. For most of history, gravitational waves were purely theoretical, predicted by Einstein, but never detected. That changed in 2015, when the LIGO Observatory detected waves from a black hole merger over 1 billion light-years away. The signal lasted less than a second, but it confirmed a century-old prediction and opened a new window onto the universe. Gravitational waves are not like electromagnetic waves. They do not interact with matter the way light does. They stretch and squeeze space itself as they pass. This makes them incredibly difficult to detect, requiring instruments sensitive enough to measure changes smaller than a proton. Yet they carry information that light cannot. They reveal the masses and spins of merging black holes, and they allow us to study regions where light is trapped. Each detection is a glimpse into the most violent events in the cosmos. Collisions so powerful they shake the very fabric of space. Hawking radiation black holes may not be entirely black. According to quantum theory, pairs of particles constantly appear and disappear near the event horizon. Normally, these particle pairs annihilate immediately, but near a black hole, one particle can fall in while the other escapes. To an outside observer, it appears that the black hole is emitting radiation. This process, called Hawking radiation, means that black holes slowly lose mass over time. The smaller the black hole, the faster it radiates. For stellar and supermassive black holes, Hawking radiation is incredibly faint, far too weak to detect. Before tiny, primordial black holes, if they exist, the effect could be significant. Over unimaginable spans of time, even large black holes would eventually evaporate completely, ending their existence in a final burst of energy. This theoretical process raises profound questions about information and entropy. If a black hole evaporates, what happens to the information about everything that fell in? This paradox remains unsolved, sitting at the intersection of quantum mechanics and gravity. Black hole mergers. Black holes can collide and merge, creating even larger black holes. When two black holes orbit each other, they emit gravitational waves that carry away energy. This causes their orbit to shrink slowly over millions or billions of years. Eventually, they spiral together rapidly, merging in a fraction of a second. The collision releases more energy than all the stars in the observable universe emit in the same time. Though almost all of it is in gravitational waves rather than light, the result is a single, larger black hole, ringing like a struck bell as it settles into its new form. These mergers are among the most powerful events in the universe. They can occur between stellar black holes and binary systems, or between supermassive black holes when galaxies collide. Each merger changes the properties of the resulting black hole, adding mass, and spin. Studying mergers helps astronomers understand how black holes grow and how they influence their gravitational wave detectors have revealed that black hole mergers are more common than once thought, occurring somewhere in the universe roughly once per minute. Each event is a fleeting but dramatic moment in the life of the cosmos. Spaghettification, falling into a black hole, would be a strange and ultimately fatal experience. As you approach, the gravitational pull on your feet would become much stronger than the pull on your head. This difference in force, called tidal stretching, would gradually elongate your body. Closer to the event horizon, the stretching becomes extreme, pulling you into a thin strand of matter. This process is called spaghettification, a somewhat whimsical name for a violent phenomenon. Eventually, you would be torn apart at the molecular level. The severity of spaghettification depends on the black hole size. Near a small black hole, tidal forces are intense, even far from the event horizon. Near a supermassive black hole, the tides are gentler, and you could cross the horizon without noticing anything unusual at first. Only later, as you fall deeper, would the tidal forces become unbearable. From the outside, observers would never see you cross the horizon. You would appear to slow down, freeze, and fade, your light shifting to longer and longer wavelengths. Time would seem to stop, even as you experience your final moments passing normally. Wormholes. Black holes have inspired speculation about shortcuts through space called wormholes. A wormhole would be a tunnel connecting to distant points in space, or even to different times. Mathematically, such structures are allowed by general relativity. They appear as solutions to Einstein's equations, bridges formed by extreme curvature of space. If they exist, they might offer a way to travel vast distances instantly, bypassing the normal limitations of speed and distance. However, wormholes face enormous challenges. They would likely be unstable, collapsing before anything could pass through. Keeping them open might require exotic matter with negative energy, something we have never observed. Even if wormholes could be stabilized, traveling through one might be dangerous, with intense tidal forces and radiation. No observational evidence supports their existence. They remain theoretical curiosities, solutions that teach us about the mathematics of spacetime, but may not correspond to real objects. Wormholes are a reminder that the equations of physics permit strange possibilities, even if nature chooses not to use them. The singularity at the very center of a black hole lies. The singularity, a point where our understanding of physics breaks down. According to general relativity, the singularity has infinite density and curvature. Space and time cease to behave in familiar ways. But most physicists believe that singularities are signals that the theory is incomplete. Quantum effects, which general relativity does not include, should become important at these scales. A complete theory of quantum gravity would likely replace the singularity with something less extreme. What might exist in place of a singularity? Some theories suggest a region of extremely high but finite density, supported by quantum pressure. Others propose that spacetime becomes grainy or foamy at the smallest scales, preventing true singularities from forming. Without a working theory of quantum gravity, we cannot know for sure. The singularity remains hidden behind the event horizon, unreachable and unobserved. It represents the ultimate frontier, the place where our current physics reaches its limit, and new principles must take over. Planet formation. Planets form from the leftover material around young stars. When a star ignites, it is surrounded by a disk of gas and dust. Within this disk, tiny grains collide and stick together, growing into larger clumps. Over millions of years, these clumps become pebbles, tin boulders, and eventually planetesimals. Objects large enough for gravity to shape them. Planetesimals continue to collide and merge, building up planets. The process is chaotic, with countless collisions reshaping the growing worlds. The type of planet that forms depends on its distance from the star and the materials available. Close to the star, it is too hot for ice to survive, so rocky planets form from metals and farther out, beyond the frost line, ice can exist, allowing much larger planets to form. These planets gather thick atmospheres of hydrogen and helium, becoming gas giants. The final arrangement of planets reflects billions of years of growth, migration, and interaction. Every planetary system tells a unique story of formation and evolution. Exoplanets beyond our solar system. Thousands of exoplanets orbit distant stars. These worlds come in astonishing variety, far exceeding what we imagined before their discovery. Some are rocky, like Earth. Others are gas giants, larger than Jupiter. Some orbit so close to their stars that their surfaces glow red-hot. Others drift in the cold outer reaches, frozen and dark. The discovery of exoplanets has transformed our understanding of planetary systems, showing that our solar system is just one example among countless possibilities. Most exoplanets are detected indirectly. When a planet passes in front of its star, it blocks a tiny fraction of the star's light. By measuring this dimming, astronomers can infer the planet's size and orbit. Another method uses the star's wobble caused by the planet's gravity. These techniques have revealed planets in orbits we once thought impossible. Hot Jupiter's massive planets, orbiting closer to their stars than Mercury, were among the first discoveries. They challenged our theories and forced us to rethink how planets form and migrate. Each new discovery expands the diversity of known worlds. Hot Jupiters. Hot Jupiters are gas giant planets that orbit extremely close to their stars. They complete an orbit in just a few days, far closer than Mercury orbits our Sun. This proximity heats them to extreme temperatures, sometimes exceeding 2,000 degrees. Their atmospheres are scorched, with winds that scream across the planet at thousands of kilometers per hour. Some are tidally locked, always showing the same face to their star, creating permanent day and night sides with drastic temperature differences. The existence of hot Jupiters puzzled astronomers. Giant planets should form far from their stars, where ice and gas are abundant, yet here they were, orbiting closer than rocky planets. The solution is migration. After forming in the outer regions, these planets spiral inward through interactions with the protoplanetary disk or with other planets. Their migration can disrupt entire planetary systems, ejecting smaller worlds or pushing them into unstable orbits. Hot Jupiters are extreme laboratories, places where we can study atmospheric dynamics, magnetic fields, and chemistry under conditions impossible to recreate on Earth. Super-Earths are planets more massive than Earth but smaller than Neptune. They represent a category that does not exist in our solar system, yet they are among the most common types of Super-Earths can be rocky, icy, or have thick atmospheres of hydrogen and helium. Their composition depends on where they formed and how they evolved. Some may be ocean worlds, covered entirely by deep water. Others may be rocky planets with extreme volcanism, or thick clouds that never clear. The potential for life on super-Earths is uncertain. A larger planet has stronger gravity, which could help retain a thick atmosphere and protect against radiation, but it might also trap too much atmosphere, creating a runaway greenhouse effect. The diversity of super-Earths means that some could be habitable while others are hostile to life. Studying these worlds helps us understand the range of planetary environments and the factors that make a planet suitable for life. Super-Earths expand the search for habitable worlds beyond simple Earth analogs. Ice worlds in the outer regions of planetary systems lie ice worlds. Planets where temperatures are so low that water, methane. These worlds can be small moons, orbiting giant planets or independent planets, drifting far from their stars. In our solar system, moons like Europa and Enceladus are ice worlds. their surfaces covered by frozen crusts. Beneath these crusts, liquid oceans may exist, kept warm by tidal heating or radioactive decay. Such hidden oceans could potentially harbor life. Ice worlds beyond our solar system are harder to study because they emit little light and are often hidden in the glare of their stars. But we know they must exist, formed in the cold outskirts where ice is stable. Some may have been ejected from their systems, becoming rogue planets drifting through interstellar space. Others remain bound, orbiting distant stars in long, slow loops. Ice worlds remind us that planets are not all warm and bright. Many exist in frozen solitude, their surfaces silent and still, yet perhaps concealing surprising complexity beneath the ice. Rogue planets, not all planets orbit stars. Some drift alone through the galaxy, untethered to any sun. These rogue planets were likely ejected from their original systems through gravitational interactions, flung into interstellar space by close encounters with other planets or passing stars. Once free, they wander to darkness, no longer warmed by starlight. Their surfaces are frozen, and their skies never see a sunrise. Yet they are not completely dead. Internal heat from radioactive decay may keep their cores warm, and some may even harbor subsurface oceans. Rogue planets are difficult to detect because they emit no light of their own. Astronomers find them through gravitational microlensing. When a rogue passes in front of a distant star and briefly magnifies its light, estimates suggest there may be billions of rogue planets in our galaxy, possibly outnumbering stars. They represent a hidden population, unseen wonders carrying their own silent histories. Some may be Earth-sized, others larger than Jupiter. Each one is a world without a home, drifting eternally through the cold dark between the stars. Diamond planets. Some planets are so rich in carbon that their interiors may contain layers of diamond. These worlds form in regions where carbon is more abundant than oxygen, leading to a chemistry very different from Earth's. Under the immense pressures inside these planets, carbon crystallizes into diamond structures. The result is a planet with a crust of graphite and a mantle of diamond, possibly thousands of kilometers thick. These exotic worlds challenge our expectations about planetary composition and structure. Diamond planets are not glittering jewels in space. Their surfaces would be dark and rocky, with no sparkling but beneath the surface, the conditions create one of the hardest substances in the universe, compressed by the weight of the planet above. These worlds are rare, but their existence shows how varied planetary chemistry can be. Studying them helps us understand how different elements combine under extreme conditions. They are reminders that planets are not all made from the same ingredients, and that the universe contains wonders we are only beginning to discover. Ocean worlds. Some planets are covered entirely by oceans, with no continents or dry land. These ocean worlds may have water hundreds of kilometers deep, far deeper than Earth's oceans. The pressure at the bottom of such oceans would be immense, possibly creating exotic forms of ice, even in the heat of the deep interior. Above the ocean, thick atmospheres might create permanent cloud cover, blocking any view of a distant sun. Life on such worlds, if it exists, would be entirely aquatic, never knowing land or sky in the way we do. Ocean worlds may be common in the universe. They could form when icy planets migrate closer to their stars, melting their frozen surfaces. Or they could develop atmospheres so thick that water remains liquid even far from the star. In our solar system, moons like Europa and Enceladus may be ocean worlds beneath their icy shells. Detecting ocean worlds around other stars is challenging because water leaves subtle signals in a planet's atmosphere. But as our techniques improve, we may find that oceans are more widespread than we imagined, raising the possibility of life in places very different from Earth. lava worlds close to their stars. Some planets are so hot that their surfaces are molten. These lava worlds have no solid ground, only oceans of molten rock that flow and churn under intense heat. Temperatures can exceed 2000 degrees, hot enough to vaporize metals. The atmosphere, if it exists, is filled with silicate vapor and exotic compounds that condense into clouds of tiny mineral grains. The day side of these planets glows red hot, while the night side may cool just enough for the surface to solidify temporarily before being reheated. Lava worlds are inhospitable to life as we know it. Their surfaces are constantly reshaped by volcanic activity and tidal forces. Some are tidally locked, creating extreme temperature differences between the day and night sides. Winds howl across the surface, driven by the temperature gradient, carrying vaporized rock and metal. These planets are laboratories for studying extreme geology and atmospheric dynamics. They show us what happens when planets form too close to their stars, baked by radiation and stretched by gravity. Lava worlds are beautiful in their violence, glowing embers in the darkness of space. Habitable zones around every star is a region called the habitable zone, where conditions might allow liquid water to exist on a planet's surface. This zone depends on the star's temperature and brightness. Close to the star, it is too hot, and water boils away. Far from the star, it is too cold and water freezes. The habitable zone is the sweet spot in between, where a planet with the right atmosphere could maintain oceans and rivers. Earth sits comfortably within the Sun's habitable zone, as does Mars. Though Mars has lost most of its atmosphere, the habitable zone is not a guarantee of life. A planet must also have the right size, atmosphere, and geological activity to remain habitable over long periods. Venus is near the inner edge of our Sun's habitable zone, but a runaway greenhouse effect has made it a hellish world with surface temperatures hot enough to melt lead. Planets in the habitable zones of other stars may face similar challenges, or they may thrive, developing conditions suitable for life. The habitable zone is a useful starting point in the search for life beyond Earth, but it is only one factor among many. Moons of gas giants. Some of the most interesting worlds in the universe are not planets, but moons. Giant planets like Jupiter and Saturn host dozens of moons, some of which may be more hospitable to life than many planets. Europa, a moon of Jupiter, is covered by a thick shell of ice, beneath which lies a global ocean. Enceladus, a moon of Saturn, has geysers that spray water into space, revealing a subsurface ocean warmed by tidal heating. Titan, Saturn's largest moon, has lakes and rivers of liquid methane on its surface, a hydrological cycle entirely different from Earth's. Moons can be habitable even if they orbit planets far outside the traditional habitable zone. Tidal heating, caused by the gravitational pull of the planet, can keep a moon's interior warm. This allows liquid water to exist beneath icy crusts, creating environments that might support life. In other star systems, moons of gas giants could offer similar opportunities. The search for life now includes not just planets but moons, expanding the number of potentially habitable worlds. Moons remind us that life may arise in unexpected places, hidden beneath ice or within the shadow of a giant planet. Binary planet systems. Some planets do not orbit stars alone but share their orbits with companion planets of similar size. These binary planet systems are rare but possible. The two planets orbit a common center of mass, locked in a gravitational dance. Tides between them can create intense heating, reshaping their surfaces and atmospheres. If the planets are close enough, they might share an atmosphere, with gases flowing between them. The sky on such a world would be dominated by the companion planet, looming large and casting shifting shadows. Binary planets challenge our understanding of planetary formation. How do two large planets end up in such close orbits without colliding or ejecting each other? One possibility is that they formed together from the same clump of material. Another is that they were captured through a rare gravitational encounter. Whatever their origin, binary planets would create unique environments. Life on such worlds, if it could exist, would experience tides far stronger than Earth's, with day lengths and seasons shaped by the orbital dance of two worlds bound together in the darkness of space. Dark matter introduction. Most of the matter in the universe is invisible. We cannot see it, touch it, or detect it with ordinary instruments. Yet we know it exists because of its gravitational effects. This mysterious substance is called dark matter, and it outweighs all the visible matter in galaxies by a factor of 5 or more. Dark matter does not emit, absorb, or reflect light. It interacts with ordinary matter only through gravity, making it incredibly difficult to study. Despite its invisibility, dark matter shapes the structure of the universe, holding galaxies together and guiding the formation of cosmic structures. The evidence for dark matter comes from many sources. Stars in the outer regions of galaxies move faster than expected, suggesting the presence of unseen mass. Galaxy clusters contain more mass than we can account for by counting stars and gas. Gravitational lensing, the bending of light by mass, reveals dark matter halos surrounding galaxies. All these observations point to the same conclusion. Most of the universe's matter is hidden, detectable only through its gravitational influence. Dark matter is one of the greatest mysteries in science, a shadow that permeates the cosmos. What is dark matter? We do not know what dark matter is made of. It could be exotic particles that interact only weakly with ordinary matter. Physicists have proposed many candidates, including WIMP, weakly interacting massive particles, and axions, hypothetical particles far lighter than electrons. Experiments deep underground search for signs of dark matter particles colliding with ordinary atoms. But so far, none have been detected. Other experiments try to create dark matter in particle accelerators, hoping to produce it in high-energy collisions. The search continues, driven by the hope of identifying this elusive substance. Another possibility is that dark matter is not made of particles at all. Some theories suggest it could be primordial black holes, formed in the early universe before stars existed. Others propose modifications to gravity itself, where the laws of physics differ on large scales, eliminating the need for dark matter. Each idea has strengths and weaknesses, and none have been confirmed. For now, dark matter remains a mystery, a placeholder name for something we detect but do not understand. Its true nature may be stranger than any current theory imagines. Dark matter. Halos. Galaxies are embedded in vast halos of dark matter. These halos extend far beyond the visible stars, sometimes reaching 10 times the diameter of the galaxy itself. The dark matter halo is what holds the galaxy together. Without it, galaxies would fly apart, their stars moving too fast to remain bound by the gravity of visible matter alone. The halo is not smooth, but a structure shaped by the history of the galaxy's formation and interactions with neighbors. Dark matter halos influence how galaxies evolve. They provide the gravitational wells into which gas falls, triggering star formation. They guide the motion of satellite galaxies, slowly pulling them inward and tearing them apart. The halo's mass determines how quickly the galaxy rotates and how it responds to encounters with other galaxies. Mapping dark matter halos is challenging because they emit no light. Astronomers infer their structure from the motion of stars and gas, and from the way they bend light through gravitational lensing. These halos are the hidden scaffolding that supports the visible universe. Dark matter halos. Dark energy introduction. Dark energy is even more mysterious than dark matter. While dark matter pulls things together through gravity, dark energy pushes space apart. It is the force responsible for the accelerating expansion of the universe, Discovered in the late 1990s, dark energy was a surprise. Astronomers expected the universe's expansion to slow down over time due to gravity. Instead, they found it speeding up. This discovery earned a Nobel Prize and fundamentally changed our understanding of the cosmos. Dark energy makes up about 70% of the universe's total energy. Its nature is unknown. It could be a property of space itself, a constant energy density that fills the vacuum. Alternatively, it could be a dynamic field that changes over time. Some theories propose that dark energy is a sign that our understanding of gravity is incomplete. Whatever it is, dark energy dominates the universe's fate. It determines whether the cosmos will expand forever or undergo some other transformation. Understanding dark energy is one of the great challenges of modern cosmology. Accelerating expansion, the universe is not just expanding, it is expanding faster and faster. This acceleration was discovered by observing distant supernovas, exploding stars that serve as cosmic distance markers. When astronomers measured the brightness and redshift of these supernovas, they found that distant ones were dimmer than expected. This suggested that the universe's expansion had sped up over time. The farther back in time we look, the slower the expansion was. Today, it is faster than ever. The accelerating expansion has profound implications. It means that distant galaxies are receding faster than the speed of light, not because they are moving through space, but because space itself is expanding. Eventually, these galaxies will move beyond our cosmic horizon, their light never able to reach us. The acceleration also affects the universe's future. If it continues, the cosmos will grow colder and emptier, with galaxies isolated in their own pockets of space. The cause of this acceleration, dark energy, remains one of the deepest mysteries in physics. The cosmological constant. One possible explanation for dark energy is the cosmological constant, a term Einstein introduced into his equations of general relativity. He later called it his greatest blunder, but modern observations suggest he may have been right after all. The cosmological constant represents the energy of empty space, a constant energy density that does not change as the universe expands. If this energy exists, it would create a repulsive force, pushing space apart and accelerating the expansion. The cosmological constant fits the observations well, but it raises difficult questions. Why does empty space have energy? And why is the amount so small? Quantum theory predicts that vacuum energy should be enormous, far larger than what we observe. This discrepancy is one of the biggest unsolved problems in physics. If the cosmological constant is correct, it means that empty space is not truly empty but filled with an energy we do not understand. This energy dominates the universe, shaping its expansion and determining its ultimate fate. Quintessence. Another explanation for dark energy is quintessence, a hypothetical field that permeates space. Unlike the cosmological constant, quintessence is not constant. It can change over time, evolving as the universe expands. This makes it a dynamic form of dark energy, one that could strengthen or weaken depending on conditions. Quintessence could interact with other fields or particles, leaving subtle signatures in the cosmos. Different models of quintessence predict different behaviors, offering many possibilities to explore. If quintessence is real, it could help explain why dark energy has the value it does. It might also affect the universe's future in unexpected ways. For example, if quintessence weakens over time, the expansion could slow down again. If it strengthens, the acceleration could increase, possibly leading to a big rip where space expands so fast that even atoms are torn apart. Distinguishing between quintessence and the cosmological constant requires precise measurements of how the universe's expansion changes over time. So far, the data does not rule out either possibility, leaving the nature of dark energy an open question The cosmological constant missing mass problem. The missing mass problem refers to the observation that galaxies and clusters do not contain enough visible matter to account for their gravitational effects. When astronomers count all the stars, gas, and dust, they find that the total mass is far less than what is needed to hold these structures together. The missing mass is dark matter, but its presence was inferred long before we understood how widespread it is. The first hints came from the motion of stars within galaxies and the speed of galaxies within clusters. This problem extends to the entire universe. When we add up all the visible matter, it accounts for less than 5% of the total energy density. Dark matter makes up another 25%. The rest is dark energy. This means that the universe we see, with all its stars, planets, and gas, is only a tiny fraction of what exists. The vast majority is invisible, made of substances we do not understand. The missing mass problem is not a failure of observation, but a deep clue that the universe is far richer and stranger than our senses reveal. Gravitational lensing. One of the best ways to study dark matter is through gravitational lensing. When light from a distant galaxy passes near a massive object, the object's gravity bends the light, creating distorted or multiple images of the background galaxy. The amount of bending depends on the mass of the intervening object, including its dark matter. By studying these distortions, astronomers can map the distribution of dark matter without seeing it directly. Lensing reveals dark matter halos, filaments, and clusters, showing how it is arranged across the cosmos. Strong lensing creates dramatic effects, such as Einstein rings or multiple images of the same galaxy. Weak lensing produces subtle distortions that can only be detected by analyzing many galaxies statistically. Both techniques have confirmed that dark matter dominates the massive galaxy clusters and shapes the large-scale structure of the universe. Gravitational lensing is a powerful tool, allowing us to weigh the unseen and trace the hidden scaffolding that holds the cosmos together. It turns darkness into data, making the invisible visible through gravity's influence on light. WIMPs and axions. Two leading candidates for dark matter are WIMPs and axions. WIMPs, or weakly interacting massive particles, are hypothetical particles that interact through gravity and the weak nuclear force, but not through electromagnetism. They would be heavy, perhaps tens or hundreds of times the mass of a proton. If WIMPs exist, they should be passing through Earth constantly, but their weak interactions make them incredibly difficult to detect. Experiments deep underground use large volumes of ultra-pure materials, waiting for the rare collision between a WIMP and an atomic nucleus. Axions are very different. They're extremely light, far lighter than electrons, and were originally proposed to solve a problem in particle physics. If axions make up dark matter, they would be incredibly numerous, forming a vast, diffuse sea, permeating the galaxy. Detecting axions requires different techniques, often involving strong magnetic fields and sensitive detectors. Despite decades of searching, neither WIMPs nor axions have been definitively detected. The search continues, driven by the hope that one of these particles will finally reveal the nature of dark matter and answer one of the universe's greatest mysteries. Dark matter detection. Detecting dark matter directly is one of the great challenges of modern physics. Experiments are located deep underground to shield them from cosmic rays and other background radiation. They use materials like liquid xenon or germanium crystals, cooled to near absolute zero, to detect the tiny energy deposited by a dark matter particle collision. These experiments run for years, sifting through data for the faint signal of dark matter. So far, no confirmed detection has been made, but the sensitivity of these experiments continues to improve. Other approaches try to create dark matter in particle accelerators, or detect it through its annihilation. When two dark matter particles collide, they might annihilate, producing ordinary particles or high-energy photons. Telescopes search for these signals in regions with high dark matter concentrations, such as the centers of galaxies or dwarf satellite galaxies. Each method offers a different window into the dark sector. The lack of detection so far does not mean dark matter does not exist. It means it is even more elusive than we hoped. Every null result narrows the possibilities, guiding the next generation of experiments. The fate of the universe, the presence of dark energy determines the ultimate fate of the universe. If dark energy remains constant, the universe will expand forever, growing colder and more dilute. Stars will exhaust their fuel, galaxies will fade, and black holes will evaporate. Eventually, the universe will reach a state of maximum entropy, a quiet, cold, an empty expanse where nothing changes. This scenario is called heat death, a slow fading into darkness over unimaginable stretches of time. If dark energy strengthens, the expansion could accelerate so much that galaxies, stars, and eventually atoms are torn apart. This is called the Big Rip, a violent end where space itself becomes unstable. If dark energy weakens or reverses, the expansion could slow and stop, followed by a contraction that pulls everything back into a dense state, possibly leading to a big crunch. Each of these futures depends on the nature of dark energy, which we do not yet understand. The fate of the cosmos hangs on this invisible force, a reminder that the universe's story is far from over. Supernovas are among the most powerful explosions in the universe. When a massive star exhausts its nuclear fuel, its core collapses in a fraction of a second. The collapse releases an enormous amount of energy, blowing the star's outer layers into space at speeds of tens of thousands of kilometers per second. For a few weeks, the supernova can outshine an entire galaxy, visible across billions of light. The explosion scatters heavy elements created in the star's core, enriching the surrounding gas with carbon, oxygen, iron, and more. There are different types of supernovas. Core collapse supernovas occur in massive stars. Thermonuclear supernovas occur in white dwarfs that accrete material from a companion star until they explode. Each type leaves behind different remnants: neutron stars, black holes, or nothing at all. If the star is completely destroyed, supernovas are essential to cosmic evolution. They disperse elements needed for planets and life, trigger new star formation by compressing nearby gas, and create exotic objects like pulsars. They are both endings and beginnings, violent yet creative, shaping the universe through their brilliant destruction. Neutron stars. When a massive star collapses in a supernova, the core can become a neutron star, one of the densest objects in the universe. A neutron star packs more mass than the sun into a sphere only about 20 kilometers across. The matter inside is compressed so tightly that protons and electrons merge into neutrons, forming a kind of atomic nucleus the size of a city. The density is so extreme that a teaspoon of neutron star material would weigh billions of tons on Earth. Gravity at the surface is incredibly strong, bending light and slowing time. Neutron stars have intense magnetic fields, sometimes trillions of times stronger than Earth's. These fields can channel particles and radiation, creating beams that sweep across space as the star rotates. When these beams point toward Earth, we see pulses of light, earning these objects the name pulsar. Neutron stars can spin incredibly fast, rotating hundreds of times per second. They are laboratories for extreme physics, where matter behaves in ways impossible to recreate on Earth. Studying them helps us understand the limits of density, gravity, and magnetism. Pulsars are rapidly spinning neutron stars that emit beams of radiation from their magnetic poles. As the neutron star rotates, these beams sweep across space like a lighthouse, creating pulses of light that we detect with telescopes. The pulses are incredibly regular, ticking with a precision that rivals atomic clocks. Some pulsars spin hundreds of times per second, their surfaces moving at a significant fraction of the speed of light. The regularity of pulsars makes them useful tools for testing theories of gravity and measuring distances across the galaxy. Pulsars were discovered in 1967 by Jocelyn Bell Bernal, who noticed regular pulses of radio waves from space. At first, the signals were so precise that they were jokingly called LGM, little green men, before being recognized as natural phenomena. Pulsars come in different types. Young pulsars are powered by their rotation and gradually slow down. Millisecond pulsars have been spun up by accreting material from a companion star. Some pulsars are part of binary systems, orbiting other stars or neutron stars. Studying pulsars reveals the behavior of matter under extreme conditions and the dynamics of collapsed stars. Magnetars are neutron stars with magnetic fields so strong they defy comprehension. The field strength can reach trillions of times that of Earth's magnetic field, making them the most magnetic objects known. This intense magnetism affects everything around them, distorting atoms, generating powerful and occasionally producing giant flares that release more energy in a fraction of a second than the sun emits in years. Magnetars are rare, with only a few dozen known in the entire galaxy. The magnetic field of a magnetar is so strong that it can affect spacetime itself, subtly altering the fabric of reality near the star. The field also stresses the neutron star's crust, causing it to crack and shift. These starquakes trigger bursts of energy that can be detected from thousands of light-years away. Magnetars are thought to form in the most massive supernova explosions, where rapid rotation and strong magnetic fields combine. Over time, the field decays, and the magnetar becomes a more ordinary neutron star. They are brief, but spectacular phases in the life of collapsed stars. Gamma ray bursts. Gamma ray bursts are the brightest explosions in the universe. For a few seconds or minutes, they release more energy than the sun will emit in its entire lifetime. These bursts come from distant galaxies, billions of light-years away, yet they are bright enough to be detected on Earth. Gamma ray bursts are thought to occur when massive stars collapse into black holes, or when neutron stars collide. The explosion produces jets of particles moving at nearly the speed of light, which emit intense gamma rays. There are two main types of gamma ray bursts: long and short. Long bursts last more than 2 seconds and are associated with the deaths of massive stars. Short bursts last less than 2 seconds and are likely caused by neutron star mergers. Both types are incredibly rare in any given galaxy, occurring perhaps once every few 100,000 years. When they occur, they can briefly outshine everything else in the observable universe. Studying gamma ray bursts helps astronomers understand the most energetic processes in the cosmos and probe the early universe. Quasars are among the most luminous objects in the universe. They are powered by supermassive black holes at the centers of distant galaxies, feeding on enormous amounts of gas and dust. As material falls toward the black hole, it forms a swirling disk that heats to millions of degrees, emitting intense radiation across the electromagnetic spectrum. Quasars can be thousands of times brighter than an entire galaxy, visible from billions of light-years away. The name quasar comes from quasi-stellar object, because they initially appeared as star-like points of light. Helium planets. Some planets may have atmospheres dominated by helium rather than hydrogen. These helium planets could form in specific conditions where hydrogen is stripped away by intense radiation or lost through atmospheric escape. Without the lighter hydrogen, helium becomes the dominant component. Such planets would have different atmospheric dynamics, With unique cloud patterns and temperature structures, they are predicted to exist around closing orbits, where stellar radiation is intense enough to drive hydrogen loss. Helium atmospheres would absorb and scatter light differently than hydrogen-rich atmospheres, creating distinct observational signatures. Detecting these planets requires careful analysis of their spectra, looking for the telltale signs of helium absorption. If found, helium planets would expand our understanding of atmospheric evolution and the diversity of planetary compositions. They would show that planets can lose significant portions of their original atmospheres and still survive, creating entirely new classes of worlds with chemistries unlike anything in our solar system. Self-interacting dark matter. Most dark matter models assume that dark matter particles interact only through gravity, passing through each other in ordinary matter without colliding. But some theories propose self-interacting dark matter particles that can collide with each other through forces unknown to us. These interactions would affect how dark matter is distributed within galaxies, potentially creating cores rather than dense cusps. At galactic centers, observations of dwarf galaxies hint at this possibility, showing dark matter distributions that differ from simple predictions. Self-interacting dark matter could solve several problems in galaxy formation. Standard models predict more small satellite galaxies than we observe, and they predict denser central regions than measurements show. Self-interaction could smooth out these discrepancies, redistributing dark matter in ways that match observations. Testing this idea requires detailed simulations and precise measurements of dark matter halos. If confirmed, self-interacting dark matter would reveal a hidden layer of physics, showing that dark matter has its own complex behavior beyond simple gravitational attraction. Warm dark matter. Dark matter could be cold, moving slowly in the early universe, or warm, moving faster. Warm dark matter would stream out of dense regions, preventing the formation of very small structures. This could explain why we observe fewer dwarf galaxies than cold dark matter models predict. The difference between cold and warm dark matter seems subtle, but it has significant effects on structure formation. Warm dark matter particles would have masses and properties different from cold dark matter, possibly making them easier to detect. Distinguishing between cold and warm dark matter requires observations of the smallest structures, such as faint satellite galaxies or variations in the cosmic microwave background. Some studies hint at evidence for warm dark matter, but the data is not yet conclusive. The nature of dark matter remains open, with multiple possibilities still viable. Each type of dark matter predicts a different universe, with different patterns of structure and different histories. Understanding which type exists would constrain theories of fundamental physics and reveal the identity of one of the universe's most elusive components. Modified gravity theories. What if dark matter doesn't exist? Some physicists propose that instead of adding invisible matter, we should modify the laws of gravity. These modified gravity theories suggest that gravity behaves differently on galactic scales than it does in the solar system. One popular idea is MONT, modified Newtonian dynamics, which changes how gravity works at very low accelerations. MONT successfully explained some galaxy rotation curves without invoking dark matter, but it struggles with larger structures like galaxy clusters. Other modified gravity theories tweak Einstein's general relativity, adding new terms or fields. These theories face significant challenges. They must match all the successes of general relativity, from GPS satellites to gravitational waves, while also explaining galaxy dynamics and cosmic structure. Most modified gravity theories have difficulty explaining the full range of observations, particularly gravitational lensing in galaxy clusters and the cosmic microwave background. For now, dark matter remains the favored explanation, but modified gravity theories persist, reminding us that our understanding of gravity may still be incomplete. The void phenomenon. Cosmic voids are not completely empty. They contain faint galaxies and dark matter, just much less than average regions. The voids themselves may be expanding faster than surrounding areas, driven by the lower density within them. This creates a cosmic pressure difference, with voids pushing outward and dense regions pulling inward. Studying voids provides insights into dark energy, the mysterious force accelerating the universe's expansion. The way voids grow and evolve depends on the properties of dark energy, making them sensitive probes of this unknown component. Voids also affect the motion of galaxies. Galaxies near void edges are pushed away, creating flows away from voids and toward dense filaments. These void-induced flows add to the complexity of cosmic motion, shaping the large-scale structure. Some theories suggest that voids play a role in determining the overall geometry of space, contributing to measurements that show the universe is flat. The void phenomenon reveals that even empty regions are dynamically important, influencing their surroundings and teaching us about the forces that shape the cosmos. Dark sector physics. Dark matter may not be alone. It could be part of an entire dark sector, a collection of particles and forces that interact among themselves but barely touch ordinary matter. In this picture, dark matter particles could experience their own dark forces, similar to electromagnetism but invisible to us. This dark sector could be as rich and complex as the visible world, with dark atoms, dark chemistry, and perhaps even dark stars. We would remain ignorant of all this complexity, detecting only its gravitational effects. The idea of a dark sector expands the possibilities for dark matter. It explains why dark matter seems to form halos and filaments without collapsing into compact objects. The dark forces could provide pressure that prevents collapse, distributing dark matter in ways that match observations. It also opens the possibility that dark matter could cool and form structures we haven't imagined. Detecting the dark sector would require creative experiments sensitive to rare interactions between dark and ordinary particles. If confirmed, it would revolutionize our understanding of the universe, revealing an invisible parallel cosmos. Tidal disruption, variability. Tidal disruption events are not uniform. The way a star is torn apart depends on its size, composition, internal structure, and the black hole's mass and spin. Some disruptions produce bright, long-lasting flares, while others are dim and brief. The star's orbit determines how much material falls into the black hole versus how much is ejected. Grazing encounters produce different signatures than head-on plunges. This variability makes each tidal disruption event unique, a cosmic experiment revealing the interplay between stellar structure and black hole gravity. Observing many tidal disruption events helps astronomers understand the statistical properties of these rare occurrences. How often do they happen? What types of stars are most commonly disrupted? How do supermassive black holes of different masses affect the process? Each event is a probe of the environment near galactic centers, regions difficult to study otherwise. The flares from tidal disruptions can outshine entire galaxies for weeks, making them detectable across vast distances. They are beacons that light up briefly before fading, each one a story of a star's final, violent encounter with a black hole. Accretion disk dynamics. Accretion disks are not static structures, but dynamic, turbulent systems. Gas within the disk moves in complex patterns, driven by viscosity, magnetic fields, and spiral waves ripple through the disk, and hotspots form and dissipate. The inner regions are hotter and denser, glowing in X-rays, while the outer regions are cooler, emitting an optical or infrared light. The disk's behavior depends on the rate of inflow, the magnetic field strength, and the properties of the central object. Understanding accretion disk dynamics is crucial for interpreting observations of black holes, neutron stars, and young stars. The disk's spectrum reveals its temperature and density structure, Variability in brightness indicates changes in the inflow rate or the formation of some disks launch jets, others produce winds, and some remain relatively stable. Theoretical models and computer simulations help astronomers predict disk behavior, but many details remain uncertain. Accretion disks are laboratories for studying matter under extreme conditions, where temperatures, densities, and magnetic fields exceed anything we can create on Earth. Orphan afterglows. Some gamma ray bursts produce afterglows that persist long after the initial burst fades. These afterglows are detected in X-rays, optical light, and radio waves, fading gradually over days or weeks. Occasionally, astronomers detect an afterglow without seeing the initial gamma-ray burst. These are called orphan afterglows, and they occur when the burst jets are pointed away from Earth. We miss the intense gamma rays but catch the broader afterglow emission that spreads in all directions. Orphan afterglows provide complementary information about gamma-ray bursts. By studying them, astronomers can estimate how often these bursts occur, even when they are not pointed directly at us. This helps constrain the total energy output and the beaming angles of the jets. Orphan afterglows also reveal the environment surrounding the burst, showing how the jets interact with gas and magnetic fields. Each detection adds to our understanding of the most energetic explosions in the universe, events that briefly outshine everything else and then fade into silence. Orphan afterglows. Cosmic rays. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. They originate from various sources, including supernovas, pulsars, and possibly more exotic events. When cosmic rays strike Earth's atmosphere, they create showers of secondary particles that can be detected on the ground. Most cosmic rays are protons, the nuclei of hydrogen atoms, but some are heavier nuclei or even electrons. The most energetic cosmic rays carry more energy than any particle accelerator on Earth can produce. The origin of the most energetic cosmic rays remains a mystery. They seem to come from beyond our galaxy, but the exact sources are unknown. Possible candidates include supermassive black holes, colliding galaxies, or other violent events. Cosmic rays play a role in galactic evolution, influencing the chemistry of the interstellar medium and affecting star formation. They also provide information about magnetic fields, since their paths are bent by magnetism. Studying cosmic rays is like studying messengers from the most energetic processes in the universe, particles that have traveled vast distances to reach us. Hypernovas are supernova explosions with energy far exceeding typical supernovas. They occur when extremely massive stars collapse, releasing energy equivalent to 100 or more supernovas. Hypernovas are rare, but they are thought to be the source of long-duration gamma-ray bursts. The collapse of the star's core forms a black hole, and jets of matter are launched from the poles at nearly the speed of light. These jets punch through the star's outer layers, creating intense beams of radiation that can be detected across the universe. Hypernovas create and disperse large amounts of heavy elements, enriching galaxies with materials needed for planets and life. They may also play a role in shaping the structure of galaxies by injecting energy into the surrounding gas. The violence of a hypernova is hard to comprehend, dwarfing even typical supernovas. If one occurred within a few thousand light-years of Earth, the radiation could affect our atmosphere and potentially harm life. Fortunately, hypernovas are extremely rare, and the nearest candidates are safely distant. They remain one of the most extreme expressions of stellar death. Kilonovas occur when two neutron stars collide. These events are less energetic than supernovas, but produce unique signatures. The merger creates a brief burst of gravitational waves, detected by observatories on Earth. It also produces a flash of light across the electromagnetic spectrum, from gamma rays to radio waves. The collision ejects material rich in heavy elements, which glows as it expands and cools. This glow, called a kilonova, can be detected for days or weeks after the merger. Kilonovas are thought to be the primary source of elements like gold, platinum, and uranium. The first kilonova was observed in 2017, coinciding with a gravitational wave detection. The event confirmed that neutron star mergers produce heavy elements and provided a wealth of data about these extreme collisions. Kilonovas are rare, occurring only once every few 100,000 years in a typical galaxy. They are both endings and beginnings, marking the deaths of neutron stars while enriching the universe with some of its rarest elements. Each kilonova is a cosmic forge, creating materials that could one day become part of new stars, planets, or even living organisms. Tidal disruption events. When a star wanders too close to a supermassive black hole, tidal forces can tear it apart. This is called a tidal disruption event. As the star approaches, the black hole's gravity pulls more strongly on the near side than the far side, stretching the star into a long stream of gas. Half of the material falls into the black hole, while the other half is flung outward. The infalling gas heats up, emitting intense radiation that can be detected from millions of light years away. These events are rare, occurring perhaps once every 10,000 years in a typical galaxy. Tidal disruption events provide valuable information about supermassive black holes. They reveal the black hole's mass, spin, and surrounding environment. The flare of light produced during the disruption can be monitored for months as the gas settles into an accretion disk. Each event is unique, depending on the star's size, composition, and the angle of approach. Observing tidal disruption events helps astronomers understand black hole feeding mechanisms and the dynamics of stars near galactic centers. They are dramatic reminders of the power of black holes and the fragility of stars that venture too close. Fast radio bursts. Fast radio bursts are brief, intense flashes of radio waves from distant galaxies. They last only milliseconds, or release as much energy as the sun emits in days. Discovered in 2007, fast radio bursts were initially a mystery, with no clear explanation for their origin. Some theories suggested colliding neutron stars, exploding black holes, or even alien civilizations. Most fast radio bursts appear only once, but a few have been observed to repeat, suggesting they come from long-lived sources. Recent observations have traced some fast radio bursts to specific galaxies and even to neutron stars with extremely strong magnetic fields. The bursts may be caused by sudden releases of energy from the magnetary surface, or by interactions between the magnetar and its environment. Despite progress, many aspects of fast radio bursts remain unclear. Why do some repeat while others do not? What triggers the bursts? As more detections are made, astronomers hope to answer these questions and understand the physics behind one of the universe's most mysterious phenomena, solar flares and CMEs. Our own sun can produce dramatic events called solar flares and coronal mass ejections. Solar flares are sudden releases of energy from the sun's surface, caused by magnetic field lines snapping and reconnecting. They produce bursts of radiation across the electromagnetic spectra, including X-rays and ultraviolet light. Coronal mass ejections, or CMEs, are even more dramatic. They eject billions of tons of plasma into space, carrying magnetic fields that can interact with Earth's magnetosphere. When a powerful CME reaches Earth, it can cause geomagnetic storms that disrupt satellites, power grids, and communications. These storms also create beautiful auroras, visible near the poles. Solar flares and CMEs a part of the sun's natural activity cycle, which peaks approximately every 11 years. Studying these events helps us predict space weather and protect technology from solar impacts. They also remind us that even our calm, steady sun can be violent. These solar storms are gentle compared to flares from other stars, which can be thousands of times more powerful. Our place in the universe, when we look up at the night sky, it is easy to feel small. Earth is a tiny planet orbiting an average star in a galaxy of hundreds of billions of suns. Our galaxy is one among trillions scattered across the observable universe. From this perspective, we are insignificant, a brief flicker in an unimaginably vast cosmos. Yet there is another way to see it. We are part of the universe, made from its materials, shaped by its forces. In us, the universe has become aware of itself. Our significance lies not in size, but in consciousness. We are the means by which the cosmos explores its own nature. Through science, we have traced our origins back to the Big Bang, mapped galaxies billions of light years away, and begun to understand the fundamental laws that govern reality. This is not a small achievement. It is a profound connection between the largest and smallest scales, between stars and thoughts. We might be tiny, but we carry within us the capacity to comprehend the vastness that surrounds us. That is no small thing. We are stardust. Every atom in your body, except hydrogen, was forged inside a star. The oxygen you breathe, the carbon in your cells, the calcium in your bones, all were created by nuclear fusion in stellar cores. When those stars exploded as supernovas, they scattered their elements into space. Over billions of years, this enriched gas collapsed to form new stars and planets, including our sun and Earth. We are not separate from the universe, but made from its substance, recycled through countless cycles of creation and destruction. This connection is not metaphorical, it is literal. The iron in your blood was created in a supernova explosion. The nitrogen in your DNA came from dying stars. When you look at the stars, you are seeing your ancestors, the furnaces that created the elements that make you possible. This perspective can be humbling and inspiring. It means we are deeply connected to the cosmos, not as observers looking at something distant, but as participants in its ongoing story. We are the universe experiencing itself. The observable universe is the region of space from which light has had time to reach us since the Big Bang. It extends about 46 billion light-years in every direction, giving us a sphere of observable space nearly 93 billion light-years across. This does not mean the universe itself is that size. It could be much larger, perhaps infinite. The observable universe is simply the part we can see, limited by the speed of light and the age of the cosmos. Beyond this horizon, galaxies exist that we will never observe, their light unable to reach us because space is expanding too quickly. As we look deeper into space, we look back in time. The light from distant galaxies has been traveling for billions of years, showing us those galaxies as they were in the past. The most distant objects we observe are nearly as old as the universe itself. In this way, telescopes are time machines, revealing the history of the cosmos. The observable universe is our window onto a much larger reality, a small patch of something possibly infinite. What lies beyond remains a mystery, one we may never fully solve. Cosmic timescales. The universe operates on timescales far beyond human experience. The Big Bang occurred 13.8 billion years ago, a span of time difficult to grasp. Stars can live for billions or even trillions of years. Galaxies take hundreds of millions of years to collide and merge. On these scales, human history is a blink, and individual lives are almost instantaneous. Yet even the longest-lived processes will eventually end. The universe itself may have a finite lifespan, at least in its current form. Understanding cosmic timescales requires humility. The universe was here long before us, and will continue long after we are gone. Yet this does not diminish our importance. We are among the first generations of humans to comprehend these scales, to map the universe's history, and to predict its future. In our brief moment, we have glimpsed eternity. That is an extraordinary gift. Cosmic timescales remind us that the universe is patient, moving slowly through vast cycles that dwarf our fleeting existence. The pale blue dot. In 1990, the Voyager 1 spacecraft, then at the edge of the solar system, turned its camera back toward Earth and took a photograph. Image Earth appears as a tiny dot, less than a single pixel, suspended in a beam of scattered sunlight. Carl Sagan called it the pale blue dot. From that distant perspective, everything we know, every person who has ever lived, every war, every triumph, every love story, exists on that tiny speck of light. The vastness of space dwarfs all human concerns. The pale blue dot is a humbling reminder of our place in the cosmos. It shows how small Earth is, how fragile, and how alone. Yet it also highlights the preciousness of our world. In all the observable universe, we know of no other place that harbors life. Our planet is the only home we have, a delicate oasis in the vast desert of space. Seeing Earth from this perspective can shift our priorities, reminding us that we share this small world and must care for it. The pale blue dot is both a scientific image and a meditation on existence. The Fermi paradox. If the universe is so vast and contains so many stars and planets, where's everyone? This question is known as the Fermi paradox, named after physicist Enrico Fermi. Given the age of the universe and the number of potentially habitable worlds, we might expect to see evidence of other civilizations. Yet we detect no signals, no structures, no signs of intelligent life beyond Earth. The silence is puzzling. Either life is extraordinarily rare, or there are barriers that prevent civilizations from becoming detectable, or we are simply looking in the wrong places or at the wrong times. Many explanations have been proposed. Perhaps life is common, but intelligence is rare. Maybe civilizations self-destruct before they can expand into space. Or perhaps they choose to remain quiet, avoiding contact. Another possibility is that we are early among the first civilizations to arise in a young universe. The Fermi paradox is both a scientific puzzle and a philosophical question. It forces us to confront the possibility that we are alone, or nearly so, in a vast and silent cosmos. Whether we find others or not, the search teaches us about ourselves. The search for life. The search for life beyond Earth takes many forms. Astronomers study exoplanets, looking for signs of atmospheres that could support biology. They analyze the light from these worlds, searching for gases like oxygen or methane that might indicate the presence of life. In our own solar system, missions explore places like Mars, Europa, and Enceladus, moons with conditions that could harbor simple organisms. SETIA. The search for extraterrestrial intelligence scans the skies for radio signals from alien civilizations. So far, the search has found no definitive evidence. But each new discovery expands the possibilities. We now know that planets are common, that liquid water can exist in many environments, and that life on Earth thrives in extreme conditions. This suggests that life elsewhere is possible, perhaps even likely. The search continues, driven by one of the most profound questions we can ask. Are we alone? The answer, whatever it is, will reshape our understanding of life, intelligence, and our place in the universe. The cosmic calendar. To understand the scale of cosmic history, astronomer Carl Sagan compressed the entire age of the universe into a single calendar year. In this cosmic calendar, the Big Bang occurs on January 1st, and the present moment is December 31st at midnight. On Tiscade, the Milky Way forms in May, our solar system in September, and life on Earth in late September. Dinosaurs appear in late December and go extinct on December 30th. All of human civilization, from the earliest cities to the present, fits into the last 10 seconds of the year. The cosmic calendar reveals how recent we are. The universe existed for billions of years before Earth formed, and life existed for billions of years before humans appeared. Our entire recorded history is an eye blink in cosmic time. This perspective can be humbling, but it also highlights how much the universe has accomplished in its long history. Stars, galaxies, planets, and life all emerged from simple beginnings through processes that took unimaginable spans of time. We are part of that story, the universe's latest chapter, still being written, the future of humanity. Humanity's future is uncertain, but our story is just beginning. In the billions of years ahead, we could spread beyond Earth, exploring the solar system and perhaps even other stars. We could transform barren worlds into habitable ones, ensuring the long-term survival of our species. Or we could remain on Earth, stewarding our planet and finding meaning in our small corner of the cosmos. Whatever we choose, the future depends on the choices we make today. The universe will continue whether we are here or not. Stars will be born and die. Galaxies will merge, and space will expand. But in us, the universe has created something unique. Minds capable of understanding its nature. That gift comes with responsibility. We must protect our planet, preserve our knowledge, and pass on the wonder of discovery to future generations. The universe is vast and old, but our story within it is still new. The future is unwritten, and the possibilities are endless. Wonder and humility. Studying the universe inspires both wonder and humility. Wonder at the beauty of nebulae, the power of supernovas, and the intricate dance of galaxies. Humility in the face of vast scales that dwarf our understanding, mysteries that remain unsolved, and forces that operate beyond our control. The universe is larger, older, and stranger than we imagined. Yet every discovery brings new questions, new puzzles, and new invitations to explore further. Science does not diminish wonder, but deepens it. Humility reminds us that we are not the center of the universe. We are a small part of a much larger whole. Yet this does not make us insignificant. We are witnesses to the cosmos, capable of appreciating its grandeur. In our brief moment of existence, we have learned to read the light of distant stars, measure the age of the universe, and glimpse the forces that shape reality. That is an achievement worth celebrating. Wonder and humility are not opposites, but companions, guiding us as we explore the universe and our place within it. Mysteries remain, despite all we have learned. The universe still holds many mysteries. We do not know what dark matter is, or what dark energy is, or how the universe began. We do not know if there are other universes beyond our own, or whether time itself is fundamental. We do not know how common life is, or whether we are alone. Each answer we find leads to new questions, deeper puzzles that push the boundaries of what we can know. This is not a failure, but a feature of science. The universe reveals itself slowly, layer by layer. Mysteries are invitations. They remind us that exploration never ends, that there is always more to discover. They keep us curious, humble, and engaged with the world around us. Some mysteries may never be solved, but the pursuit itself is valuable. It pushes us to develop new technologies, refine our theories, and challenge our assumptions. The universe is vast, and our understanding is limited. But every mystery we confront is an opportunity to learn, to grow, and to see the cosmos with fresh eyes. The privilege of awareness. We are among the few structures in the universe capable of understanding it. Stars burn without knowledge. Galaxies collide without thought. But in us, matter has organized itself into patterns that can reflect, question, and comprehend. We are the universe looking at itself, a rare and precious phenomenon. This awareness is a gift, one we did not ask for, but have received nonetheless. With it comes the privilege of exploring reality, of asking questions that no other known species can ask. This privilege also carries weight. We are responsible for using our awareness wisely, for preserving the knowledge we have gained, and for passing it on to future generations. We are temporary custodians of understanding, brief flickers of consciousness in a vast, mostly unconscious cosmos. Our awareness may be rare, but it is real. It allows us to appreciate beauty, ponder existence, and feel connected to something far larger than ourselves. In T-sense, we are not just observers of the universe, but participants in its ongoing story. The beauty of science. Science is often seen as cold or purely rational, but it is also a source of profound beauty. The equations that describe gravity, the images of distant galaxies, the elegance of physical laws, all carry a beauty that rivals any art. Science reveals patterns hidden beneath the surface, symmetries that connect disparate phenomena, and simplicities that unify complexity. The universe is not only vast, but also deeply ordered, governed by principles we can understand. This beauty is not subjective. It exists in the structure of reality itself, waiting to be discovered. When we uncover a new law of physics, or see a distant nebula for the first time, we are witnessing something real, something that existed long before we arrived and will continue after we are gone. The beauty of science lies in its honesty. It does not invent truths, but reveals them. Each discovery is a gift, a glimpse into the hidden architecture of the cosmos. This beauty inspires awe, curiosity, and a desire to know more. The beauty of science, a moment of rest as our journey through the universe comes to a close. Allow yourself to rest. Let the vastness sink in, not as a burden, but as a comfort. The universe is large, and you are small, but you are part of it. You are made from its elements, shaped by its forces, and filled with its wonder. There is no need to understand everything tonight. The cosmos will still be here tomorrow, waiting patiently, as it has for billions of years before you existed, and will for billions more after. Take a deep breath. Feel the weight of your body, the softness of your surroundings. The stars are still shining, galaxies are still turning, black holes are still bending space. All of this continues, whether you are awake or asleep. You do not need to hold it all in your mind. Let it go. Let the universe carry you, as it has always done. You are safe here, cradled in the fabric of spacetime, drifting gently toward sleep. Gratitude. Thank you for taking this journey through the universe. Thank you for your curiosity, your patience, and your willingness to explore the unknown. The universe is a gift, and so is your ability to understand it. Even a little. Every star you see, every fact you learn, every question you ask is a connection between you and the cosmos. This connection is real and deep. It ties you to the oldest processes and the largest structures, making you part of something far greater than yourself. If this journey brought you peace, wonder, or a moment of calm, then it has succeeded. If it stirred new questions or curiosity, even better. The universe is not a distant abstraction, but a reality you live within, a story you are a part of. Carry that awareness with you. Remember that you are stardust, that the atoms in your hand were forged in ancient stars, that you are both small and significant, brief and eternal. Thank you for listening. Thank you for being here. Nature of time. Time is one of the most mysterious aspects of the universe. We experience it as a steady flow from past to future, yet physics tells us time is more flexible than it seems. Einstein showed that time is relative, flowing at different rates, depending on motion and gravity. Near a massive object, time slows down. At high speeds, clocks tick more slowly. This means there is no universal now, no single moment shared across the cosmos. Time is woven into the fabric of spacetime, inseparable from the dimensions of space. Before the Big Bang, our equations suggest that time itself did not exist. This is difficult to imagine because we think of time as fundamental, as something that has always been. But if time began with the universe, then asking what came before may be meaningless. Some theories propose that time is emergent, arising from deeper processes we do not yet understand. Others suggest time could be cyclic, with the universe expanding and contracting in endless rhythm. The nature of time remains one of physics' deepest puzzles, a mystery that touches every moment of our existence. Quantum fluctuations. In the quantum world, nothing is truly still, even in perfect vacuum. Particles and antiparticles constantly appear and disappear, borrowing energy from the void for the briefest instant before vanishing again. These quantum fluctuations are real, measured in laboratories, and they have profound implications. In the early universe, these tiny fluctuations were stretched to cosmic scales by inflation, becoming the seeds of galaxies and large-scale structure. The universe we see today grew from quantum uncertainty, from random jitters and fields that filled the infant cosmos. Quantum fluctuations blur the line between something and nothing. They show that empty space is not empty, but filled with ceaseless activity. Virtual particles pop into existence, interact, and disappear before they can be directly observed. Yet their effects are measurable, influencing the behavior of atoms and the vacuum itself. Some physicists speculate that the entire universe could be a quantum fluctuation, a vast temporary borrowing of energy that will eventually return to the void. This idea is speculative, but it highlights the strange and probabilistic nature of reality at its deepest levels. The horizon problem. When we look at opposite sides of the sky, we see regions separated by distances so vast that light has never had time to travel between them. Yet these regions have nearly identical temperatures, as measured in the cosmic microwave background. This is puzzling. How can two regions that have never communicated look so similar? This is called the horizon problem, and it challenged cosmologists for decades. The solution is cosmic inflation, a brief period of exponential expansion that occurred in the universe's first moments. Inflation stretched space so rapidly that regions now far apart were once close enough to reach thermal equilibrium. After inflation ended, these regions were carried apart by the continuing expansion. This explains why the universe looks so uniform on large scales. Without inflation, the horizon problem remains unsolved, requiring implausible fine-tuning of initial conditions. Inflation is now a cornerstone of cosmology, supported by observations of the cosmic microwave background. It shows that the universe's large-scale smoothness is not a coincidence, but a consequence of processes that occurred long before stars or galaxies existed. Antimatter mystery. In the early universe, matter and antimatter were created in equal amounts. When they met, they annihilated, producing pure energy. If perfect symmetry had been maintained, all matter and antimatter would have destroyed each other, leaving only radiation. Yet, we exist, and the universe is filled with matter, not antimatter. This asymmetry is one of the great mysteries of physics. Somehow, there was a tiny excess of matter, about 1 part in a billion. This small imbalance allowed matter to survive and form stars, planets, and life. What caused this asymmetry? We do not fully know. The answer likely involves subtle differences in how matter and antimatter behave under certain conditions. Experiments have detected small violations of symmetry in particle interactions, but not enough to explain the observed imbalance. Understanding this mystery is crucial because it explains why anything exists at all. The universe could have been empty, filled only with photons from ancient annihilations. Instead, a tiny imperfection gave rise to everything we see. We are the descendants of that imbalance, products of an ancient asymmetry written into the laws of physics. Recombination era, about 380,000 years after the Big Bang. The universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. This event is called recombination, though it was actually the first time atoms formed, not a recombination in the usual sense. Before this moment, free electrons scattered photons constantly, making the universe opaque. Light could not travel far before being absorbed and re-emitted. After recombination, photons could finally move freely, and the universe became transparent. The light released at that moment is what we observe today as the cosmic microwave background. Recombination marks a turning point in cosmic history. It separated the radiation-dominated era from the matter-dominated era. Before recombination, radiation pressure was strong enough to influence the motion of matter. After recombination, matter began to clump under gravity, eventually forming the first stars and galaxies. The patterns imprinted on the cosmic microwave background during recombination revealed the conditions of the early universe, including the density of matter, the amount of dark matter, and the geometry of space. This ancient light is a fossil from an era we can never visit, a snapshot of the cosmos in its infancy. Stellar winds. Stars do not just shine, they breathe. Throughout their lives, stars emit streams of charged particles, called stellar winds. These winds carry mass and energy away from the star, slowly eroding its outer layers. In small stars like the Sun, the wind is gentle, a steady outflow that shapes the space around the star. In massive stars, the wind is fierce, blowing at thousands of kilometers per second and carrying away significant amounts of mass. Over millions of years, these winds can strip a star of its outer envelope, exposing deeper layers and altering its evolution. Stellar winds shape the environments around stars. They create bubbles in the interstellar medium, pushing gas and dust outward. They can trigger star formation by compressing nearby clouds. They also enrich space with elements created in the star's core, spreading heavy elements throughout the galaxy. When stars die, their winds become even stronger, puffing off layers of gas that form beautiful planetary nebulae. These winds are the star's last breath, a gentle dispersal of material that will one day become part of new stars, planets, and perhaps life. Brown dwarfs revisited. Brown dwarfs occupy a strange middle ground between planets and stars. They form like stars, collapsing from clouds of gas, but they never gather enough mass to sustain hydrogen fusion. Without fusion, they glow only with the heat left over from their formation, gradually cooling over billions of years. The smallest brown dwarfs are barely larger than Jupiter, while the largest approach the size of small stars. They are dim, often invisible light, but they glow faintly in infrared wavelengths. Studying brown dwarfs helps astronomers understand the boundary between planets and stars. What defines a star? Is it mass, composition, or the ability to fuse hydrogen? Brown dwarfs challenge these definitions. Some have planetary systems of their own, with smaller objects orbiting them. Others drift alone through the galaxy, dark and solitary. Despite their name, brown dwarfs are not brown but appear red or magenta in infrared images. They are failed stars, but they are also laboratories for studying atmospheric dynamics, magnetic fields, and the physics of substellar objects. The gene's mass for a cloud of gas to collapse and form a star. It must overcome internal pressure. Gravity pulls the cloud inward, but gas pressure, turbulence, and magnetic fields push outward. The minimum mass required for gravity to win is called the gene's mass, named after physicist James Jeans. This mass depends on the cloud's temperature and density. In cold, dense clouds, the gene's mass is small, allowing many low-mass stars to form. In hot or diffuse clouds, the gene's mass is larger, favoring the formation of fewer, more massive stars. The gene's mass explains why stars form in clusters rather than individually. When a large cloud becomes unstable, it fragments into pieces, each of which can collapse on its own. The resulting cluster contains stars of many different masses, from tiny red dwarfs to massive blue giants. The distribution of these masses follows a pattern called the initial mass function, which seems to be similar across the universe. Understanding the gene's mass and related physics helps astronomers predict where and how stars will form, both in our galaxy and in distant systems. Urbigaro objects, young stars are often violent, ejecting jets of material at high speeds. When these jets collide with surrounding gas, they create glowing shock waves, called Urbigaro objects. These objects are bright in optical and infrared light, appearing as irregular patches or knots of emission near newborn stars. They move through space at hundreds of kilometers per second, plowing into the interstellar medium and creating turbulence. Urbigaro objects are transient, lasting only a few thousand years before fading as the jets weaken or change direction. Studying Urbigaro objects provides insights into the earliest stages of stellar life. The jets are driven by the interaction between the star's magnetic field and the surrounding accretion disk. Material falling toward the star is funneled along magnetic field lines and ejected from the poles. This process helps the star shed angular momentum, allowing more material to fall inward. Urbigaro objects also reveal the structure of the birth cloud, lighting up regions that would otherwise remain dark. They are signposts of star formation, markers of the chaotic processes that transform gas clouds into shining suns. Urbigaro objects. Metallicity in astronomy. Any element heavier than helium is called a metal. This unusual definition means that oxygen, carbon, and iron are all metals. The abundance of these elements in a star, called its metallicity, reveals its history. Stars born early in the universe have low metallicity because few heavy elements existed then. Stars born more recently, like the Sun, have higher metallicity, enriched by the deaths of previous generations. Metallicity affects how stars evolve, how planets form, and even the colors of galaxies. High metallicity stars can form rocky planets more easily, because the necessary elements are abundant. Low metallicity stars may have fewer planets, or planets made of different materials. Metallicity also influences stellar lifetimes and the types of remnants they leave behind. Astronomers use metallicity as a clock, tracing the chemical evolution of galaxies over billions of years. By measuring the metallicity of stars in different regions, they can reconstruct the history of star formation, supernova explosions, and gas flows that shaped the galaxy we see today. Dwarf galaxies. Not all galaxies are grand spirals or giant ellipticals. Many are small, faint systems called dwarf galaxies. These galaxies contain only a few million to a few billion stars, far fewer than the hundreds of billions in the Milky Way. Dwarf galaxies are common, possibly outnumbering large galaxies by 10 to 1. They are often found orbiting larger galaxies as satellites, held by gravity in long, slow orbits. The Milky Way has dozens of known dwarf companions, including the Magellanic Clouds visible from the southern hemisphere. Despite their small size, dwarf galaxies are important. They may be the building blocks from which larger galaxies formed, merging over time to create the systems we see today. They also contain clues about dark matter. Some dwarf galaxies appear to have more dark matter than visible matter, making them excellent laboratories for studying the invisible substance. Others seem to lack dark matter entirely, challenging our understanding. Dwarf galaxies remind us that galaxies come in all sizes, and that even the smallest systems can teach us about the universe's history and structure. Tidal tails. Tidal tails. When galaxies interact, gravity can stretch them into long, graceful streamers called tidal tails. These tails are made of stars, gas, and dark matter pulled away from the galaxies by tidal forces. They can extend for hundreds of thousands of light years, arcing through space like cosmic ribbons. Tidal tails are evidence of past encounters, markers of gravitational violence that reshaped entire systems. Over time, the tails may fade as their stars disperse, or they may collapse to form new structures, including dwarf galaxies. Tidal tails provide valuable information about galaxy interactions. By studying their shapes and motions, astronomers can reconstruct the history of the collision, determining when it occurred and how the galaxies approached each other. Tails also reveal the distribution of dark matter because the visible matter traces the gravitational field. Some of the most beautiful images in astronomy show galaxies with sweeping tails, frozen moments in a slow-motion cosmic dance. These features remind us that galaxies are not isolated, but interact, merge, and evolve through gravitational encounters. Starburst galaxies. Some galaxies experience intense bursts of star formation, producing new stars at rates hundreds of times faster than the Milky Way. These are called starburst galaxies, and they are among the brightest and most active systems in the universe. Starbursts can be triggered by galaxy collisions, which compress gas and ignite waves of star formation. They can also occur when gas flows into the central regions of a galaxy, perhaps driven by interactions with other galaxies or by instabilities in the disk. Starburst galaxies are brilliant in infrared light because the newly formed stars are often hidden inside thick clouds of dust. The dust absorbs ultraviolet light from young stars and re-emits it as infrared radiation. Starbursts are short-lived, typically lasting a few tens of millions of years before the gas is exhausted or blown away by supernova explosions. After the starburst ends, the galaxy quiets, leaving behind a population of aging stars. Studying starburst galaxies helps astronomers understand how galaxies grow and how bursts of activity shape their evolution. Galactic cannibalism. Large galaxies grow by consuming smaller ones, a process called galactic cannibalism. When a dwarf galaxy wanders too close to a giant, tidal forces stretch and tear it apart. Its stars are scattered into long streams that gradually merge with the larger galaxy. Over time, all evidence of the dwarf's existence fades, absorbed into the giant's halo. This process is ongoing. The Milky Way is currently consuming several dwarf galaxies, including the Sagittarius dwarf, which is being pulled apart and dispersed across the sky. Galactic cannibalism is a major driver of galaxy growth. Most large galaxies have consumed dozens or even hundreds of smaller systems over their lifetimes. Each merger adds mass and can trigger bursts of star formation or feed the central black hole. The process also explains the complex structure of galactic halos, which contain remnants of past meals. Streams of stars wrap around the galaxy like ghostly ribbons, traces of ancient cannibalism. Studying these streams helps astronomers reconstruct the galaxy's merger history and understand how structure forms in the universe. Ultra-diffuse galaxies. Some galaxies are so faint and spread out that they are nearly invisible. These ultra-diffuse galaxies have the mass of typical dwarf galaxies, but are stretched across regions as large as the Milky Way. Their stars are so thinly distributed that they barely stand out against the night sky. Some ultra-diffuse galaxies are found in dense galaxy clusters, where tidal forces may have puffed them up. Others exist in isolation, their origins more mysterious. The existence of ultra-diffuse galaxies challenges our understanding of how galaxies form. Why are some galaxies so diffuse while others are compact? One possibility is that they formed in unusual environments, perhaps in low-density regions where gas remains spread out. Another is that interactions with other galaxies or with dark matter halos altered their structure. Despite their faintness, ultra-diffuse galaxies may contain significant amounts of dark matter. Studying them helps astronomers explore the diversity of galaxies and the processes that shape their appearance. Black hole jets. Some black holes launch enormous jets of particles and energy from their vicinity. These jets are powered by the immense energy released as matter falls toward the black hole. Magnetic fields twist and focus the material, accelerating it to nearly the speed of light and shooting it outward in narrow beams. The jets can extend for thousands or even millions of light years, far beyond the galaxy itself. They create huge lobes of radio emission, visible to radio telescopes across the universe. Black hole jets influence their surroundings in profound ways. They heat the gas around the galaxy, preventing it from cooling and forming new stars. This feedback process helps regulate galaxy growth, limiting how large galaxies can become. Jets can also trigger star formation by compressing gas in their path. Understanding how jets form and what powers them remains a challenge. They involve complex interactions between gravity, magnetism, and plasma physics, processes that push the limits of our theoretical understanding. Jets are among the most energetic phenomena in the universe, visible reminders of the power concentrated near black holes. Intermediate mass black holes. Between stellar black holes and supermassive black holes lies a mysterious middle ground. Intermediate mass black holes, if they exist, contain hundreds to thousands of solar mass. They are too massive to form from single stars, but too small to be the supermassive black holes at galactic centers. Astronomers have found tantalizing hints of these objects in dense star clusters and dwarf galaxies, but confirmed detections are rare. Their existence would fill a gap in our understanding of black hole populations. How intermediate mass black holes form is unclear. They might grow from stellar black holes that merge repeatedly in dense environments, or they could be remnants of the first generation of stars, which were much more massive than stars today. Another possibility is that they are the seeds of supermassive black holes, the cores around which galactic centers grew. Finding and studying intermediate mass black holes would help answer fundamental questions about how black holes of all sizes form and evolve over cosmic time. Black hole information paradox. The black hole information paradox is one of the deepest puzzles in theoretical physics. According to quantum mechanics, information cannot be destroyed, but when something falls into a black hole, it seems to disappear forever, crossing the event horizon and vanishing from the outside universe. If the black hole eventually evaporates through Hawking radiation, what happens to the information? Does it re-emerge, encoded in the radiation, or is it truly lost, violating quantum principles? This paradox has sparked decades of debate. Some physicists argue that information is preserved, encoded on the event horizon, or released gradually through subtle correlations in Hawking radiation. Others propose more radical solutions, such as modifications to quantum mechanics, or the existence of remnants left behind after evaporation. The paradox touches on fundamental questions about the relationship between quantum mechanics, gravity, and the nature of information. Resolving it may require a complete theory of quantum gravity, one that unifies these principles in ways we do not yet understand. Primordial black holes. In the earliest moments of the universe, density fluctuations could have been large enough to collapse directly into black holes without forming stars first. These hypothetical objects are called primordial black holes, and they could have masses ranging from tiny fractions of a gram to thousands of solar mass. Unlike stellar black holes, primordial black holes would not be made from collapsed stars, but from the intense conditions of the early universe. If they exist, they could account for some or all of the dark matter. Primordial black holes are difficult to detect because they do not emit light. Small ones may have evaporated through Hawking radiation long ago, leaving no trace. Larger ones could still exist, drifting through the galaxy invisibly. Astronomers search for them using gravitational lensing, looking for brief flashes when a primordial black hole passes in front of a distant star. So far, no confirmed detections have been made, but the search continues. Discovering primordial black holes would open a window into the universe's first moments and potentially solve the mystery of dark matter. Firewall paradox. The firewall paradox emerged from attempts to resolve the information paradox. If information must be preserved and released through Hawking radiation, then the radiation must be entangled with particles inside the black hole. But quantum mechanics forbids one particle from being entangled with two others simultaneously. This creates a contradiction. One proposed solution is that a wall of high-energy particles, a firewall, exists just inside the event horizon, destroying anything that crosses. This firewall would prevent paradoxes, but at the cost of contradicting general relativity, which predicts that crossing the horizon should be smooth. The firewall paradox reveals tensions between quantum mechanics and general relativity. It suggests that one of these theories, or our understanding of them, is incomplete. Some physicists argue that firewalls do not exist and that information is released through more subtle mechanisms. Others propose that the event horizon itself is not what we think, perhaps replaced by a quantum fuzzball or other exotic structure. The paradox remains unresolved, a sign that black holes still challenge our deepest theories about reality. Tidally locked worlds. Some planets orbit so close to their stars that tidal forces lock them in place, always showing the same face to their sun. One side experiences eternal day, baked by constant starlight, while the other remains in perpetual night, frozen in darkness. The boundary between these extremes, the terminator, is a narrow band where temperatures might be moderate enough for liquid water. Tidally locked worlds challenge our assumptions about habitability, creating environments unlike anything on Earth. The atmosphere of a tidally locked planet would behave strangely. Heat from the day side could drive powerful winds that circulate around the planet, redistributing warmth. But if the winds are too weak, the night side could become so cold that its atmosphere freezes, falling as snow and leaving the day side exposed to intense radiation. Some models suggest that life could survive in the terminator zone, where conditions are more stable. These planets are common around red dwarf stars, making them important targets in the search for life beyond our solar system. Trojan. Planet. In some planetary systems, planets may share the same orbit, separated by about 60 degrees in a configuration called Trojan planets, named after the Trojan asteroids in our solar system, which share Jupiter's orbit. These planets would be held in stable positions by the gravitational balance between the star and another planet. Trojan planets have not been definitively detected, but they are allowed by physics and could exist in systems with the right conditions. If Trojan planets exist, they would create fascinating dynamics. The two planets would never collide, held apart by gravitational forces. Observers on one Trojan planet might see the other as a bright, steady light in the sky, neither rising nor setting. The stability of Trojan orbits makes them interesting for long-term habitability. They offer yet another way that planets can arrange themselves, expanding the diversity of possible planetary systems. Detecting Trojan planets would require careful observations of stellar wobbles or transit timing variations, techniques that are improving with each new generation of telescopes. Planet migration. Planets do not always stay where they form. Interactions with the protoplanetary disk, with other planets, or with the star itself can cause them to migrate inward or outward. This process, called planet migration, explains many of the unexpected configurations we observe in exoplanetary systems. Hot Jupiters, for example, likely formed farther out and migrated inward over time. Migration can be smooth and gradual or violent and chaotic, depending on the system's dynamics. Migration has profound effects on planetary systems. It can disrupt the orbits of other planets, ejecting some into interstellar space or sending them crashing into the star. It can also deliver water-rich bodies to the inner system, potentially making rocky planets habitable. Understanding migration is crucial for predicting where habitable worlds might form. Our solar system shows evidence of migration. Jupiter and Saturn likely moved inward before shifting outward again, a process that shaped the orbits of the outer planets and scattered comets into the inner system. So combinary planets, some planets orbit, not one star but two, circling a binary star system in a figurate or circular path. These circumbinary planets experience two sunrises and two sunsets, with complex patterns of light and shadow. The star's motion creates intricate gravitational dynamics, making circumbinary orbits more complicated than those around single stars. Yet observations show that such planets are not rare. Several have been detected, proving that planets can form and survive in binary systems. Circumbinary planets challenge planet formation theories. The gravitational influence of two stars stirs the protoplanetary disk, making it harder for planets to grow, yet they manage, suggesting that planet formation is more robust than we thought. These worlds would experience unusual climates, with seasons determined by the changing distance to two stars. If life could exist on a circumbinary planet, it would adapt to these complex rhythms. Studying these systems helps astronomers understand the full range of environments where planets can form. Relativistic beaming jets from black holes and neutron stars move at speeds close to the speed of light. At these relativistic speeds, light emitted from the jet appears brighter and more concentrated than it would if the jet were moving slowly. This effect, called relativistic beaming, can make jets appear hundreds or thousands of times brighter when pointed toward us. It also causes the radiation to be shifted to higher energies. Beaming explains why some quasars and gamma-ray bursts are so luminous. We are looking directly down the barrel of a jet moving near light speed. Relativistic beaming has profound implications. It means that the number of observed sources depends on their orientation. Most jets are not pointed at us, so we miss them entirely, or see only faint afterglows. Only a small fraction of jets happen to be aligned with Earth, creating the bright sources we detect. Understanding beaming helps astronomers estimate the true number of active galactic nuclei, gamma-ray bursts, and other jet-producing phenomena. It reveals that the universe is filled with energetic events, most of which remain invisible to us simply because they are not pointed in our direction. Supernova light curves. The brightness of a supernova changes over time, rising sharply, peaking, and then declining. This pattern, called a light curve, contains information about the explosion's energy, the mass of ejected material, and the elements produced. Different types of supernovas have distinct light curves. Type Ia supernovas, which occur in white dwarfs, have remarkably consistent peak brightness, making them useful as distance indicators. Core collapse supernovas from massive stars show more variety, with light curves shaped by the star's mass and composition. Studying light curves helps astronomers classify supernovas and understand the physics of the explosions. The decline rate reveals how quickly the ejecta expands and cools. Bumps and wiggles in the curve hint at interactions with surrounding material or the presence of radioactive elements. By analyzing thousands of supernovas, astronomers have discovered that some dimming occurs not just from expansion but from dust forming in the ejecta, blocking light. Each supernova light curve is a fingerprint, a unique record of a star's violent death, written in the language of changing brightness. The anthropic principle observes that the universe's properties seem finely tuned for life. If the strength of gravity were slightly different, stars wouldn't form. If the electromagnetic force were weaker, atoms wouldn't hold together. If dark energy was stronger, galaxies would never condense. This fine-tuning raises questions. Is it coincidence, design, or something else? One explanation is the multiverse. If countless universes exist with different properties, we naturally find ourselves in one where life is possible because we couldn't exist in the others. The anthropic principle is controversial. Some see it as a cop-out, avoiding explanations by appealing to selection effects. Others argue it is a legitimate insight, showing that observer selection matters in cosmology. Weak versions simply note that our existence constrains the universe's properties. Strong versions suggest that the universe must be capable of producing observers. The debate touches on philosophy as much as physics, asking whether the universe's apparent fine-tuning requires explanation or is simply a brute fact we must accept. Conscious observers' consciousness remains one of the greatest mysteries. How does matter, arranged in specific ways, give rise to subjective experience? How do neurons firing create thoughts, feelings, and awareness? Science has made progress understanding the brain's structure and function, but the hard problem of consciousness, explaining why there is something it is like to be us, remains unsolved. Some philosophers argue that consciousness may be fundamental, a basic feature of the universe like mass or charge. The universe is vast, and as far as we know, mostly unconscious. Stars burn without awareness. Galaxies collide without thought. Yet in tiny pockets, on planets like Earth, matter has organized itself into patterns capable of reflection. This makes consciousness rare and precious. We are the universe's way of knowing itself, however briefly. Whether consciousness will spread beyond Earth, carried by descendants into space, or remain confined to this single world, is a question for the future. For now, we are witnesses, aware of the vastness around us. The long-term future. In the far future, the universe will look very different. Trillions of years from now, star formation will cease as galaxies run out of gas. The stars that remain will age and die, one by one, until only the longest-lived red dwarfs remain. Eventually, even they will fade, leaving behind white dwarfs, neutron stars, and black holes. Galaxies will become dark, filled with stellar remnants that emit no light. The universe will be colder, emptier, and quieter than it is today, entering an era unlike anything we have seen. Yet even in this distant future, processes will continue. Black holes will slowly evaporate through Hawking radiation, taking trillions of years to disappear completely. Protons, if they are unstable, may decay, turning matter itself into radiation. The universe will approach maximum entropy, a state of equilibrium where nothing changes. This is called heat death, a cold, dark end. But it is not violent or sudden. It is a gentle fading, the universe settling into silence after eons of activity. The long-term future is quiet, but not empty, filled with remnants and the memory of what once was. The gift of existence. Existence itself is a mystery. Why is there something rather than nothing? Why does the universe exist at all? These questions lie at the boundary of science and philosophy. Physics can describe how the universe evolved from its earliest moments, but it cannot explain why those moments occurred. Some theories propose that the universe emerged from a quantum fluctuation, a brief borrowing of energy from the void. Others suggest that existence is necessary, that nothingness is unstable and spontaneously generates reality. Whatever the answer, the fact remains. The universe is here, and so are we. We did not ask to exist, but we do. This gift of existence, however brief, allows us to experience, learn, and wonder. We can gaze at stars, ponder the infinite, and feel connection to the cosmos. We can create meaning, build civilizations, and pass knowledge to future generations. The universe's existence is improbable and astonishing, and our presence within it even more so. This is not a burden, but a privilege, an opportunity to witness the grandeur of reality. Final reflection as we close this journey through the cosmos. Remember that you are part of something far greater than yourself. The atoms in your body were forged in ancient stars. The energy that powers your thoughts comes from processes that began billions of years ago. You are connected to the universe, not as an outsider looking in, but as a participant, a living expression of the cosmos's capacity for complexity and awareness. This connection is real, deep, and unbreakable. The universe is vast, old, and mysterious. It contains wonders beyond counting, from the smallest quantum fluctuations to the largest cosmic structures. Much remains unknown, and much may always remain unknown. But that is not a failure. It is an invitation. Each mystery is a door waiting to be opened. Each question a path forward. As you drift to sleep, carry with you the knowledge that you are part of this grand story. A brief but beautiful chapter in the universe's long unfolding. Rest well, knowing the cosmos continues, patient and eternal. Good night.